Hey guys, this is your master teacher Nabamita, and today we are going to start as well as end with the chapter structure of atom. It is going to be about 4 to 5 hours, but I promise that you will be able to understand each and every topic that can come in your board exam or in JEE mains or in JEE advanced. So watch the session very carefully so that you get at least 8 to 12 marks in JEE mains or in advanced, because we can expect 2 to 3 questions from this chapter. So let's get set go towards the board.
So, the story of structure of atoms starts right now. Now, let's go and check it out. How many topics are there? And by the way, I hope you can see this 1 month, 11th will be done. That means in this month, July month, we are going to complete the whole of class 11th. And then we are going to start with 12th one shots as well. But before that, we are going to do topic wise lecture of class 12. Anyway, all of these later on. Let's check out how many topics are there. Now, as you can see, there are many topics. Yes, let's go one by one. So, initially we will do discovery of subatomic particles. Now, is this important in with respect to JEE mains or advanced? Not at all. However, these initial some of the topics are very important to understand all of these. Hence, we have to do it. Okay. So, like I said, it is not important in JEE or JEE mains or JEE advanced. However, we have to study it. So, discovery of subatomic particles, that means electrons, protons and neutrons. These are the things that we are going to study. Then we start with the atomic models. Thompson's atomic model, Rutherford's atomic model, and then there is a topic called distance of closest approach. That is very important for JEE mains, actually JEE advanced. However, then developments leading to Bohr's atomic model. This is very important. Photoelectric effect, dual behavior of electromagnetic radiation is important. Atomic spectra, Bohr's model for hydrogen atom, towards quantum mechanical model of the atom. All of these that you see, orbitals and quantum numbers, shapes of atomic orbitals, energies of orbitals, filling of orbitals in atom, electronic configuration of atoms. Apart from these, there are also certain topics that are inside these, like Schrodinger's wave equation, like Heisenberg's uncertainty principle, Auber principle, Hund's rule, Pauli's exclusion, all of these. So, in this session, you will be, once you are done with the chapter, you will actually feel like, I'm done with everything. And now, I'm not going to waste any more time. Let's start with discovery of electron. So, whatever structure that we know of right now was not how we thought to be, right? At certain point, especially in the very beginning, Sir Dalton, he thought that no, atoms are the smallest particles and they are indivisible. But later on, he was proven to be wrong, right? With the first subatomic particles being discovered was this. This was the experiment, right? Now, what exactly is this? This is called as a cathode ray tube. What is it called? This is called as a cathode ray tube. Bole to CRT. You know, in the olden days, I mean, when I was growing up, we did not have this flat screen TV or, you know, OLED, the curved TV or LED TV. We did not have all of these. We had those bulky kind of TV where you had to go there and change the knobs and everything, right? In those days, we used to call the TV to be CRT TV. It's called as basically nothing but this cathode ray tube, right? Cathode ray tube. That's exactly what it was. Now, actually it looked like this. However, we will not be able to understand things from here, which is why this makes it more easier for us to understand. So, in this cathode ray tube, if you look very carefully, it might look very complicated. Actually, there is nothing much. There is a cathode here. Yes, there is a cathode here, as you can see. Do you see this? This is the cathode. That's the negatively charged electrode. And here is your anode, right? Anode is the positively charged positively charged electrode. And here there is a vacuum pump. With this, what they did was they removed most of the air particles. Now, if you remove the air particles, do you understand that air is at a very low pressure, right? So, can I just write it down that air here is at low pressure. Air is at low pressure. All right. And why low pressure? If the question comes in your mind that why have we taken air to be at low pressure, that's because you know that air is a bad conductor of electricity, isn't it? So if you take many air particles, it will be tougher for you to make them conducting, correct? So that is why we take air at low pressure, that is maximum amount of the air particles we have removed, and we have used a high voltage generator here, okay? So high voltage, low pressure, and when the electricity flows inside this tube, what happens is we start seeing that electrons have come out. But do we actually see it? No, electrons are not visible, yeah? You cannot see them really, but you can see the behavior of them. You can see the effect that they are producing. And what is that effect? Furthermore, what we did was we used a fluorescent screen here. When we used a fluorescent screen here, these electrons, they were, or these cathode rays, the rays that are coming out of the cathode, they strike this surface and you could see something, you could see a spark, you could see something coming out of it at this spot. You could see that there was a light, there was a spark, something coming out of it, which means that there was definitely something that was coming out of the cathode. That proved our point even more. So let's just check out what exactly have we learned here. In this case, we have learned that the cathode rays, they start from the cathode and they move towards the anode, correct? This is exactly what we read. The cathode, they start from the cathode, they move towards the anode, right? Like this, they come, okay? Alright. These rays, they are not visible. That's exactly what I said. They are not at all visible. But you can see the behavior, you can see the effect that they are producing. Okay? Yeah? Cool? Cool with this much, right? Now read the third point. In the absence of electrical or magnetic field, they travel in straight line. But if there is an electric field or a magnetic field, what happens? That we will study in the next slide. But before that, yes, you have understood that without any electrical field or magnetic field, see how they are traveling here, straight lines, straight lines, straight lines. Got it? Yeah. Now in the presence of magnetic field and electric field, what happens is they start behaving like a negatively charged particle, and that told us that these rays, they have certain particles which are basically negative, and we know today that electrons are negatively charged particle, right? So proven, everything is proven, hence proof, thus proof, we got it, right? Fifth point is the characteristic of these cathode rays, they do not depend upon the materials of the electrons. Whatever you take here, cathode and anode, whatever you take here, it doesn't matter on them, right? It doesn't depend on what gas do you have here. What gas you have here doesn't matter. Any gas that you take, all the particles, they behave like this. Okay? Alright. So that means that electrons do not depend on the material of the electrodes. It doesn't depend on the gas that you have taken inside. Got it? Yeah? Great. Now moving on from here, so I told you, right, how do they behave in case of an electric and a magnetic field. Now if you take an electric field, so this part that you see, this is electric field, yes, these are the electric field, yes, and this north, south that you see, this is the magnetic field. Now do you see that this is the ray, right, this is the ray here. So if you see, if you look carefully and imagine that this is a 3D picture, so basically what is happening is these, the electric field, the magnetic field and the rays, they are all perpendicular to each other, which means, let's take a look at it. So if this is my remote, this is my ray, this is my cathode ray, this is my electric field, the pen is the electric field, and this is my magnetic field. This is my magnetic field. Understanding? All of them are 90 degree, 90 degree, 90 degree perpendicular. Exactly. So that's what we did, right? Now when we have taken it like this, when we applied electrical field, the rays, they traveled like this and they hit the spot A. When we have taken the magnetic field, we saw that the rays, they bent and they hit the position C. But without any of these field, we saw that they are hitting the point B. That means without any field, they are traveling straight line. Remember, they are traveling in a straight line with electric field, they are bending and they are hitting the A position. With magnetic field, they are bending and they are hitting the C position. Okay, so this is what we see. So what? We have seen something great, but from here, what do we understand? Well, let's understand that from here we understand the deviation of particles from their path in the presence of electric or magnetic field, it depends upon three things. What are these three things? Number one is the magnitude of the negative charge. What is magnitude? Magnitude is basically the number, the strength of the negative charge. What is magnitude? Once again, magnitude means the strength, okay? The strength of the negative charge. Then number two factor is the mass of the particle. Yes, what is the mass of the particle? Higher is the mass, greater is the deflection. If the mass is higher, then the deflection becomes higher. And it also depends on the strength of the electrical or magnetic field. So when you change the magnitude of the electric or the magnetic field, you saw that there was a change. There was a change. Okay? Alright. Now from here in your NCERT, you will also find that charge to mass ratio. What is charge to mass ratio? E by ME if I take. It was found out to be, let's check it out guys, okay, let's check it out, 758,820, 8820, that's it. Is that all? No, into 10 to the power 11, okay, into 10 to the power 11 coulomb per kg, alright, correct. So this is your electron, this is your charge by mass ratio, alright, got it. Now since electrons are negatively charged, what happens? The charge on the electron is considered to be minus E, okay. We know that electrons are negatively charged, so we take the charge to be minus E, got it here, yes. So the E by ME ratio was found to be this, it was found to be this, clear everyone, great, okay. So what did I say once again? ME is the mass of electron. You know what? Let's write it down here. ME is basically the mass of electron. Alright. Yes. I hope my handwriting is visible, right? Mass of electron in mass of electron. And E is what? What is E? What is E? I just told you. I just told you guys. And E is the magnitude of the charge, okay? E is the magnitude of the charge. Okay? This is in coulomb and this is in kg. Alright? Yes? Got it? Clear. Now what happened? There was this another person called Millikan. Right? What did Millikan do? Millikan only did this. Millikan only did this. So Millikan did an experiment called oil drop method. What happened in this oil drop method? Basically, he took something like this, okay? He took a tube like this and here there was an oil atomizer. What is this oil atomizer? Have you seen in the olden days in rickshaws you had those, you could just press like this and you used to make a sound like a horn. Pa, poo, pa, poo, they used to do. Exactly. So this is that oil atomizer and here in this part you have actually kept some oil. So when you press this, what happens is droplets of oil go into this chamber, okay? Droplets of the oil go into this chamber. Yes? Very small, tiny droplets, right? Now when they reach this top plate, this is where you have, these are basically the electrodes that you have, okay? You have connected, yes, you have connected some source here, so electricity is flowing through here. Now when they reach this top part, the top plate, after passing through the top plate and at this point of time, some X-rays were also sent into the chamber, okay? Yes, X-rays were also sent into the chamber and now this oil droplets, they are passing through here. The oil droplets have come here, right? The oil droplets have come here and the X-rays are also made to pass through this chamber. Now what happens is, when the oil droplets they collided, with the charges, they started to behave like a charged particle. Now in this case, the particles' movement were dictated by gravitational force, obviously, because it is coming down, as you can see, gravitational force. Now it also started to act like a charged particle now, correct? Yes, everybody. So if it started to behave like a charged particle, so that means there are some other forces also, of course, electrical field now. Yes, electrical field or electrical force. Apart from that, because they are moving, so there is also drag force that is acting on them, okay. So these three forces are acting on them and they are coming down. Now you can see through this microscope or through this eyepiece here, right? You can see through this eyepiece. And what happened was, when you increase the current flowing through it or you decreased it, the particles were either retarded or they accelerated. Like either they were stopping, they were refraining from movement, or they started to move very fast, okay. Let's take a look at it. So this is exactly what happens. See, the oil droplets are falling here, X-ray is passing through. The moment they hit it, you can see through here, see, and they started behaving like a charged particle, So when you increase the current, see, you increase the current, the speed increased. See this arrow, you increase the current, the speed increased. As you decrease it, the speed of the particles moving in the chamber decreased. I hope this is clear. Yes. So Millikan concluded that the magnitude of electric charge Q on the droplets, it's always an integral multiple of the electric charge. So an integral multiple of the electric charge E, that is Q is equal to N multiplied with E. Let me write that down, okay. Let me write that down. Yeah, I'm going to write it here. So take a look at it. I said that Millikan concluded that the magnitude of electric charge of electrical charge Q on the droplets, okay, on the droplets is always an integral multiple of the, I hope this is visible. Is it going to down? Anyway, I'll be giving you the PDF, so don't worry about it, okay. I'll be giving you the PDF. An integral multiple of the electrical charge. Okay, all right. This means that Q is equal to N multiplied with E. This is our formula. Got it clear? Okay. All right. So all of these are clear. So sorry, I was about to fall. Anyway, moving on. Now let's understand charge on electron. What is the charge on electron? Yes, what is the charge on electron? Let's check it out. What is the charge on electron? I'm pretty sure that you all can tell me. Yes, it is minus 1.6 into this. Yes, Coulomb. All right. Yes. And the present value, this is what we came out with. Yes, and the present value today is 1.602176, okay, 1.602176 into 10 to the power what? Same thing, yeah? Okay, this is the present value. Now if you have to find the mass of the electron, remember what we did was E by ME and all of that, right? We did this E by ME. Now if we have to find out the mass of electron that Thomson had given, that was given by Thomson, right? So mass of electron, if we have to find out, what will we do? What will we do? Let's take that ME is equal to, okay, ME is equal to, let's do E by ME. So this value we already know, this value we know from here. So if we put it 1.602176 into 10 to the power minus 19C, divide it by what? What was the value here? The value was 1.758820 into 10 to the power 11, right? So 1.758820 into 10 to the power 11 coulomb per kg, right? So when you solve this, you find a value which is 9.1094 into 10 to the power minus 31. What is the mass? The mass is 9.1094 into 10 to the power minus 31. That is the answer. Coulomb cancel, so this will be kg. This is the answer, okay. This is the value of mass of electron. Got it? So till now we are done with electrons completely. Now when we go forward, we have to understand discovery of proton. So basically you take the same thing, take the same discharge tube, okay, take the same discharge tube, you have a fluorescent screen coating here, right, and here one thing that you have done is you have taken a perforated anode. What have you taken? Perforated. What do you mean by perforated? By perforated, we don't mean anything, but it's just a fancy name for holes. Basically in the anode there are chotu small holes in it, okay. So you have taken a perforated anode, and the same way you have high voltage but you have low pressure, right, low pressure here, low pressure you have, and you have high voltage, correct. So low pressure, high voltage, the current passes through, and from cathode, obviously as usual there are cathode rays that are coming out. But now what happens is, we saw here that although the electrons were coming out, but after some time, after they have went through this perforated anode and they met the fluorescent coating, then they started to come out from this side. Somehow we saw that from the anode, like they went from here like this, they went from here like this, right? But after hitting them, then what happened was the direction somehow changed, okay? What happened? The direction somehow changed now. And because the direction changed, we started to call them canal rays. What did we start to call them? We started to call them canal rays or the anode rays. So if you are thinking that we started to call them anode rays because they were coming from anode, actually no, they don't come out from anode. They come from here, they come from the cathode, but after hitting the fluorescent coating, then they go back, and that's why we started to call them anode rays, okay. So what are the things that we saw here? We saw that the mass of the positively charged particles, this time it depended upon the nature of the gas. In the last one, in the discovery of electron, we saw that it did not depend on the gas, but here it did depend on the nature of the gas. Alright, yes, moving on from here, now what happens? See, the charge to mass ratio of the particle also dependent on the gas from where they originate. The charge by mass ratio also dependent on the gas. You getting my point? Then, some of the positively charged particles, they carry a multiple of the fundamental unit of electrical charge. The positively charged particles, they carry a multiple of the fundamental unit of electrical charge. So whatever is the electrical charge, you basically now put a n. You put a multiple of it, and that's the result that you get. And this time we also saw that the behavior of these particles in the magnetic or the electric field was opposite to what we saw in the discovery of electrons. So that means these are opposite to the charge that electrons were carrying. So electrons were carrying negatively charged, as we know. Protons are carrying positive charge. Now let's go and take a look at the discovery of neutrons also. So who discovered neutrons? If you want to know, it was discovered by Chadwick. It was discovered by Chadwick. Okay? Yes, Chadwick discovered in 1932. So in 1932, what he did was alpha particles that were coming out from polonium. Do you know what is alpha particles? If you do not know, alpha particles are basically those that have two positive charge okay? Alpha particles have two positive charge. Alright, yeah, okay. 2 positive charge and mass 4. 2 positive charge, mass 4. Mass has to be 4, right? So the alpha particles that were coming from polonium, okay, the alpha particles that were coming from, alpha particle source is what? Source is polonium. You can write it down, although this will not come in the exam, but this is just good to know, general knowledge, okay. So the alpha particles that were coming out from polonium were made to be bombard on beryllium. They were made to, you know, hit the beryllium, all right. And when they hit the beryllium, okay, what did we see? We saw neutrons coming out, okay. We saw neutrons coming out. So basically, if I write it like this, okay. Now, why did I write 0 here? Any idea why did I write 0 here? Because neutrons, as the name suggests, they are neutral in nature. Yes, they are neutral in nature. No charges. They have no charges. Cool. But they have mass. They have mass, but they have no charges. Hence, this is how we have written them. Alright. So with this note, all the subatomic particles we are done with. All the discoveries of subatomic particles are there. The properties of fundamental resource, this is something that you should know. I have just, you know, copied and pasted it from NCERT. This is there in your NCERT. As you will see that the symbols are EPN, that is electron, proton, neutron. Absolute charges are there, relative charges are there. This is what we take, and mostly this is what we will take to calculate right now. Mass per kg is also given to you. Mass per U is also given to you. Approximate mass per U is also given to you. Shall we solve a question? Let's solve a question. So the question is the ratio of charge to mass of an electron in coulomb. This is not Columbus, this is coulomb. Coulomb per gram was determined by J.J. Thomson, right? Yes. That E by ME value thing. Now he determined this ratio by measuring the deflection of cathode rays in electric and magnetic field. What value did he find for this ratio? What value did he find? The answer is obviously 1.7588. So 7588 we can definitely keep it as 1.76 into 10 to the power 8 coulomb per gram. This is per gram. But what we learnt was per kg. So from per kg, if you convert it to gram, it will be, instead of 10 to the power 11, you can write it as 10 to the power 8. Done? Great? Amazing. So done and dusted. You guys are getting good at it. Moving on to the next question. How many number of electrons are present in a particle which carries a charge of 5.5 into 10 to the power minus 16 coulomb? This is very easy, guys. What you have to, the formula that you have to use is N is equal to, see, Q is equal to NE, right? Yes, what we learned was, wait a second, let me write it down properly. Yeah. So what we learned is Q is equal to N multiplied with E. So that means N is equal to Q by E. Agreed? Agreed everyone? Great. Now what we know is, see, what is given to us? What is given to us? In a particle which carries a charge of 5.5 into 10 to the power minus 16. So 5.5 into 10 to the power, what is going on? Right? This is what I write. And what is my E value? Everybody knows 1.6 into 10 to the power minus 19, right? So 1.6 into 10 to the power minus 19, correct? Now when you calculate this, what is the answer that you will get? You find that out. Find that out. Find that out, okay? This is just simple calculation. I think you'll be able to do it. But any which ways, the answer is option A, alright? The answer is option A. Moving on. The increasing order for the values of charge by mass is, understand the question. They are asking you basically to find the charge by mass ratio of neutron, charge by mass ratio of alpha particle, charge by mass ratio of proton, charge by mass ratio of electron. This is what you have to find out. Alright. Now once you have found that out, then see which one is the greatest. Let's do it. Now see, the charge by mass ratio of neutron is equal to what? It will be 0, no? Charge is 0. So anything that is 0 divided by 1 is equal to 0. So n is 0. Now let's find it for proton, let's say. Yeah, neutron then proton. For proton, what will it be? 1. What will it be? Charge is 1. Mass is also 1. So 1. Yes. For electron, let's do it. Charge is 1 divided by, what is mass? What is mass? Mass will be around 1 by 1837. So this is very, very, very small. And for alpha, if I find out, for what is alpha? Alpha is 2 by 4. Alpha is 2 by 4. So first is this. This is our number 1. Yes. Then comes this. This. Then comes this. Yes. And then finally is this. This has the lowest value. This has the lowest value. So I think it's option D. I think it's option D. Yeah. Option D is the correct answer. Got it? Cool. Now, let's study about atomic number and mass number. So you all understood that the discovery of subatomic particles, where we found out that there are electrons, there are protons and there are neutrons. Electrons are negatively charged, protons are positively charged, neutrons are neutral. Okay. Please listen to the basics carefully. I know you might think that, ma'am, this is very easy. Why are you taking so much time? Bit up, please. Just give it a little bit time, revise it properly, only then we will be able to fast complete the chapter, okay? So, atomic number. What is atomic number? Everybody knows it. Come on, don't tell me that you do not know. Let me change the color of the pen though. Let's make it yellow. Yes. So, the number of protons present in the nucleus is equal to atomic number. What did I say? The number of protons present in the nucleus is equal to atomic number. So how do we denote atomic number? Atomic number is denoted with the letter Z. Okay. How is it denoted? It's denoted with the letter Z. So let's write it down here. What is atomic number? Atomic number is number of protons. Number of protons in the nucleus of an atom. Alright. This is also equal to, because atom is a neutral, right? For the neutrality of the atom, sometimes we can also write it as the number of electrons alright. This is what we are going to write. Now, next thing is mass number. What is mass number? Protons and neutrons present in the nucleus are collectively known as nucleus. Yes, protons and neutrons that are present in the nucleus are collectively known as nuclides actually. Yes, but anyway, yeah. So, the total number of nucleons, alright. Oh, did I say nuclides? No, nucleons. Sorry, my bad, yeah. So, the total number of nucleons is termed as mass number. Let's write it down. Is termed as mass number. What are nucleons? Alright, this is it. So basically, if I have to write down the formula now like this, what is mass number? Mass number is denoted with capital A. Alright, how do we denote it? Capital A. That is basically number of protons plus number of neutrons. Cool? Yes, this we have understood. Now this number of protons can also be basically your Z and this is your N, alright. So atomic number plus number of neutrons is going to give you mass number. Don't be confused. Mass number is denoted with capital A and atomic number is denoted with capital Z. Okay? Yes. So if you are thinking that ma'am these are very easy and I don't want to learn, guess what? This is the session. This is the only session that you need to watch for your boards, for your MSET, for your IIT JEE mains, for your JEE advanced. Anything and everything will be covered here. So please sit back, relax, take some popcorn, get a notebook and a pen and write it down while I am teaching you so that you don't have to watch it later and make the notes. Alright. Now we have understood the composition of atom, right? Composition of atom is understood by us that atom has electrons, neutrons and protons, and we have understood that what is atomic mass number, what is atomic number, what is mass number. So the composition of an atom can also be written as basically X. This is the symbol. Here you write down the mass number and here you write down the atomic number. Okay? Alright everybody. Let me write that down again very clearly. What did I say? I said that this is the symbol. This is the symbol of the element. Here is the atomic mass number and here is the atomic number. So what did I say? X is the symbol of element. A mass number, as you know, and Z atomic number. This is how we basically denote an element. Okay, this is how we denote an element. But coming to the fact that there are several other terms that we are going to use in this chapter, so let's learn that all one by one. First one is isotopes. What are isotopes? I think everybody, all of you know it, right? What are isotopes, Vicha? What are isotopes? Come on. Isotopes are basically atoms with identical atomic number but different mass number. Yes? What are isotopes? Atoms with identical atomic number. but different mass number. Correct? Yes, we have understood this. Amazing. Now what are isobars? Let's understand that also. What are isobars? Isobars are the atoms with same mass number but different atomic number. Yes, what is the example that I can give? Example would be 14C6 and 14,7N. Note down, guys. Yes, this is a possibility. Okay, this is a possibility. Actually, no, it cannot be 12. It cannot be 14. I think it should be 12 only, no? 6, 7. No, clear. This is fine. This is fine. Yeah, no mistakes. I think I'm sorted. Cool. Okay. Now, moving on. Are these the only two things that we need to know? No. If we are going to go for JEE mains, and there are several other terms also that we need to know. Third term. Let's take isotones. What are isotones? Isotones are basically the elements having the same number of neutrons. That is, when you do mass number minus atomic number, the number that you will get, yes, isotones, elements having same number of neutrons. Let's write it down. Okay, this is your isotones. Now comes isosters. Okay, now comes another term called isosters. What is this now? This you might be hearing for the first time. Okay, isosters are species that have the same number of atoms and electrons. Okay, species that have same number of atoms and electrons. All right, yes. Next comes isodiphers. Yes, isodiphers. Let's write that down. What are isodiphers? Isodiphers are basically the elements that have the same number of, let's check it out, okay? A minus 2Z, okay? Now, why am I writing this symbol, not a bracket? That means that we are also always going to take the positive value, okay? We are also always going to take the positive value. Now comes another term called isoelectronic species. What are isoelectronic species? Isoelectronic species, what do they have? They have the, tell me. Species having the, species or the elements which have the same number of electron, okay? So, species or elements having the same number of electrons. All right, great. There are some more terms. There is something called as paramagnetic and diamagnetic. Just know it. Yes, just know it. Although we will not need it in this chapter, but just know it, because paramagnetic and diamagnetic also supposedly come because of the unpaired electrons, right? So species, those who have non-zero unpaired electron, or the species that have unpaired electrons, okay? Or elements, species or elements, right? Let's write both, species or atoms, actually, not elements, species or atoms having at least one unpaired electron. Okay, this is your paramagnetic. And finally, the last one is, of course, diamagnetic. What is diamagnetic? Species or atoms which do not have, which have zero unpaired electron, basically. So let's write it down. So species, atoms have zero unpaired electron. That means they do not have any unpaired electrons. Okay, they do not have any unpaired electrons. All the electrons that they have are actually paired with each other. So these are all the terms that you should know. You don't have to like really remember the definition, but just know that what are these, because these will these are the terms that will be used in your exam and you will have to know the answer, correct? So with this note, now let's go to the Thompson's atomic model. That means we are starting with the new section of the chapter, that is atomic model. So Thompson's atomic model, I think everybody knows, this is also called as the plum pudding model or the watermelon model. Yes, what is this called as? The plum pudding model. Now obviously we are Indian, so we do not know what exactly is plum pudding, because let's just face the truth bomb here. We don't eat plum pudding. Who is plum pudding? Yeah, I mean plum cake, sure, during Christmas only, that too. So anyway, Thomson was a Englishman, right? He was an Englishman, and obviously he was born and brought up by eating plum pudding, right? He was eating a lot of plum pudding, especially during the Christmas, and that's when an idea struck in his mind, and he was like, you know what, the atom probably looks like the plum pudding, right? He said that the whole thing is of a positive sphere. This whole thing is positive sphere, and in between there are electrons engraved in it. What do we mean by engraved? Have you seen how watermelon seeds are just engraved in it? Like you actually have to scoop it out with your nail or a spoon or something like that. Exactly. So that how the seeds are present in the watermelon, that exactly is called as engraved. Okay. Yeah. Look it up. Look it up in the dictionary. Anyway. So basically he said that the whole red part, if you imagine a watermelon, or you have seen it, so imagine if this is a watermelon, the whole red part is basically the positive sphere, and he said that the seeds, they are the electrons. Now obviously this was a great model. I know it doesn't sound very great, it sounds very stupid. However, this did prove that, this did explain the neutrality of the atom. But apart from that, when Rutherford came into picture and when he did this experiment, the famous experiment, Rutherford's gold foil experiment, which you have also learnt about it in your junior classes, but just a recap quickly. So this was the source. This is called as a collimator. Yes, what is it called? It is called as a collimator. So from the source, alpha particles were bombarded into gold foil. Why was gold foil taken? You know that it is malleable. It is highly malleable. So you could beat it up. Just beat it, right? When you just beat it, it keeps getting thinner and thinner. So you could take a very thin sheet where there were very, there were what, 1,000 atoms. That was the thickness of the sheet, right? So when he took this, right, and then the results that he saw, right? The results that he saw. And there was also a zinc sulfide, you know, there was also a zinc sulfide, what do you call, collar kind of thing, yes, collar kind of thing. And then the results that were seen was Rutherford and his students. Actually, Rutherford was the teacher. There were two students, their name was Hans Geiger and Ernest Marsden. Yeah. Now, Geiger's name you have heard. In physics, you will be studying about something called as Geiger-Müller counter. Yeah, you will be learning about it. So that Geiger is the same Geiger. Yes. Anyway, so Hans Geiger and Ernst Marsden, they actually did the experiment because obviously he was the teacher, he took all the credit away, right? So they did this experiment where a stream of high energy alpha particles from a radioactive source was directed at the thin foil. Yes, the thin foil was 100 nanometer. Right. Now, the thin gold foil, it had a fluorescent zinc sulfide screen around it. I said collar, it's a screen basically. And whenever the alpha particles, they struck the screen, a tiny flashlight was produced at a point. Now, check out what actually happened, right? So, basically the alpha particles, they were coming, the alpha particles were coming. See how some of them deflected with a smaller angle, and some of them, they came near the nucleus and they went exactly in the same straight line as they had come here. So basically what he observed was, he observed that most of the alpha particles, they just passed straight. Without anything, they just came and they just went ahead. Nothing happened, they just went ahead, okay. Then there was some where there was a small deflection, they went away. They bent away from the straight line with a very small angle. Then there were some who took a large deflection, yes, and there were some which just turned back as it is. So basically the conclusion was that most of the space in the inside of an atom is actually empty, right? Yes. And alpha particles, because they were positively charged from they were positively charged helium nuclei, right? They can be deviated from a positive charge, correct? We know it from a very basic point of view. We know that like charges repel like charges, unlike charges, they attract each other, right? That's exactly what happened here, yes? So there definitely must be some positively charged region inside the atom which repelled the alpha particle. That was the conclusion. Very smart, right? Now, only few particles, they deviated. Yes, and that means that the positively charged region inside the atom was actually very less. So I can also write it that if let's say that radius of nuclei is actually much lesser than the radius of the atom. This I can write it, right? Yes. So the positively charge of the atom, the positive charge of the atom is concentrated in a minuscule region. Minuscule means it's very small region. Yes, that is called as a nucleus. So the radius of the nucleus is 10 to the power minus 15 meter and that of an atom is 10 to the power 10. So if the atom is in angstrom, then the radius of the nuclei is in Fermi. You get my point? You get the you get the difference? Yeah. So it's like this, okay. Now what happened was, of course it was a great stepping stone, right? It was a great milestone in the whole chemistry's history. However, there were limitations. There definitely were limitations. But let's just let's go into that a little later. Let's understand that an atom consists of the tiny positively charged nucleus at its center. The nucleus contains positively charged particles. Almost entire mass of the atom is actually focused in the nucleus and all the positive charge is concentrated in the nucleus. Yeah. Okay, everybody? Getting my point? Yes? Nucleus? Alright? Okay? Yes. Electrons, they revolve around the nucleus in circular paths called as orbits. Yes, and this model resembles the solar system, right? In circular paths, basically they revolve around concentric circles, right? So basically if this is your nucleus, then these are the path of your electrons, right? The electron and the nucleus, they are held together because of electrostatic charges. There is positive charge, there is negative charge. So what will happen? Electrostatic force of attraction. Positive and negative, unlike charges, they were getting attracted. Electrostatic force of attraction was there, which is why the atoms was not falling apart. It was right there. It was properly held together. But there was, of course, limitation. What happened in the limitation? So you understand that it does not obey the Maxwell's theory of electrodynamics. Now you were probably asking, ma'am, what is this Maxwell's theory of electrodynamics? Nothing, very easy. So what Maxwell said that, so if an electron is moving around the nucleus, right? If something is moving around like this in a circular orbit, that means that when the electron is moving, it is emitting energy. Because it's an accelerated motion. It is getting accelerated and it's moving. It's continuously changing the direction, right? In a circular orbit, you are always changing the direction. So when you are always changing the direction, it's an accelerated motion. If it is an accelerated motion, that means that the electron is supposed to emit energy. And constantly, if it is emitting energy, that means there will be a time when it does not have energy and it will fall into the nucleus. And everything and anything is gone. The atom will not be stable like how we see it. That's what Maxwell said. So according to this theory, a small charged particle, if it is moving around an oppositely charged center, it is continuously losing energy. And if an electron does so, that means that there has to be a time when it is like, it falls. But is that happening? If that happens, then we have to question the whole existence of matter. You get my point? So if electrons are constantly radiating energy, then it is a spectra. Then its spectra has to be continuous. But that's again not the case. Later on we found out that no, spectra is not continuous. It was actually line. Atoms were giving line spectra. We will learn about it. We will learn about it. Okay. So there was a limitation. But now there is a topic called as distance of closest approach. This is very important from JEE mains and advanced point of view. Very important. Please do read it. Okay, please do read it. So basically you have to understand that distance of closest approach, the literal meaning of this sentence says that, the literal meaning of the sentence is basically what it's saying is, alpha particle is coming, right? It is traveling, and then it sees something and it turns back, right? What happens when you are bunking a class in your school? Yeah, let's just say that you went to the canteen, you went to the playground and everything. You wanted to go to the canteen and the playground, obviously to play something or just pass the time, right? So you came out of the washroom and you're going like, with full-fledged like Salman boy, you're going like this, and then what happened? You see principal, so you are like, you went, this is what you did, correct? Exactly. Now check out what is happening here. Yeah, check out what is happening. So imagine that this is my alpha particle. This is my alpha particle, right? And this is my gold foil. This is my gold foil. Au, gold. This also has positively charged nucleus, right? This has a positively charged nucleus. So what is actually happening is, this is coming. Yes, it still keeps coming. And then what happens, at certain point, it's like, no, I'm not gonna go beyond this point. It says that I am not going to go beyond this point. Yep. Yes. And then what it does is, it just turns back and comes this side. So initially it started to come out like this. It went. At this point, it came back. It's like, nah, I'm not going beyond this. Now when the alpha particle started moving, would you understand that there is kinetic energy because it started to move? Also, it will have potential energy, correct? It will have kinetic energy and potential energy. And even at this point, it will have kinetic energy plus potential energy, right? Right, everybody? Clear? Great. So what is the kinetic energy here? Kinetic energy is definitely half mv square. Correct? What is the potential energy? Is K Q1 Q2 by R. Correct? Yes? Okay. This Q1 and Q2, let it be like this only, or I can also write this Q1, Q2 as, just take a look at it. I can also write it as K 2E, yes, K 2E into ZE divided by R, okay. I can also write it as 2E ZE divided by R, which will make it to be K 2 ZE square by R. Clear? Alright. Now where do I get the R from? I can call this distance to be R. Okay, I can call this distance to be R. Alright. Yes, so here it is coming out with some velocity. The alpha particle is coming out with some velocity. This is my R distance, and from here to here, if I take, my R is, let's say, R dash. This is a very large R. This is very large. Okay. So here I can write half mv square. This is my kinetic energy. Now what is my PE? My PE here will be, my dear students, please take a look at it. I just wrote that P is kz e square, k2e, wait a second, yes, this is my PE. My PE is k2ze square divided by R. But I just told you that R is very large, infinity. If that is the case, then I can write it to be 0. Yes, why did I do that? Because R is very large, so I am writing it as 0. This will be equal to, now see, the alpha particle is going. It came till here, and then what happened? Acha, what do you do when you are going? You saw the principal, you stood like this for some time, and then you turn back, right? It wasn't like this, and it doesn't happen like this, right? It doesn't happen like this. You stood there, you saw the principal, and then you turned back. So at certain point, your velocity was 0, right? Your velocity was 0. Yes. So that means at this point, I can write my kinetic energy to be 0, and my potential energy will be k z e square divided by R, and here 2. Yes. So that means that I can write it to be half mv square is equal to 2kze square divided by R. Got it? Yes. Or I can also write it to be R is equal to, what will be my R? My R will be, see, this 2 will go here, so 4kze square divided by mv square. Got it? Yeah? Is this clear, everybody? Is this clear? Is there anything that gets cancelled somewhere? Anything that gets cancelled somewhere? This is what it is? Correct. So now write down what is what. Now write down what is what. Okay. What is my m? What is my m? M is the mass of particle. Okay. Let's write it down here. M is mass of particle. Yes. Okay. All right. What is K? K is equal to 9 into 10 to the power 9. Correct? Yes. What is Z? Z is the atomic number. Z is the atomic number. Alright? Yes. Then what is E? E also you know, E is 1.6 into 10 to the power minus 19 C. Yes. Then what is V? V is velocity. V is velocity. Alright. So this is what is distance of closest approach. Please do remember it. It is very important for JEE Mains and JEE Advanced. Cool. Alright, everybody. Understood? Distance of closest approach. Now moving on from here. Okay. Moving on from here. I think I did everything here only. I was supposed to do bits of it here. But chalo. So when the alpha particle approaches the nucleus to make a head-on collision with the nucleus, the alpha particle approaches the nucleus, yes, it approaches the nucleus until what? Until R is equal to 4k z E square divided by mv square. This is your formula, okay? This is your formula. Understood everybody? Got it? Clear? Chalo, now let's do a question here. Alright, let's do a question here. Come on. Read the question everybody. Read the question. The question is, how many neutrons are there in 88 strontium 38? This is very easy. All you have to do is 88 minus 38 is equal to 88 minus 38 is equal to what? 50. So the correct answer is of course option B. Got it? Alright? Yes. Amazing. Moving on to the next question. Which of the following conclusions could not be derived from Rutherford's alpha particle scattering experiment? Most of the space in the atom is empty. This was true. Radius of the atom is about 10 to the power minus 10 in 10 to the power minus 10 meter, while that of nucleus, this is also true. Electrons move in a circular path of fixed energy called orbits. Electrons and the nucleus are held together. This is the correct answer. He never said anything about orbits. He never said anything about orbits. Did he? He didn't. Yeah. Fixed energy called orbits, that he did not say. Orbits, yes, he said that concentric circles like the solar planet system and everything, but he did not say anything about fixed energy called orbits, right? So option C is the correct answer. Great. Next question guys, which of the following pair is isodiaphers? What was the formula? The formula was A minus 2Z. Correct? Not bracket, it has to be straight line. Okay, alright. So let's do it for each one of them then. What is the mass number? The mass number for the first option is C, 14 minus 2 into 6. So 2 6 are 12, 14 minus 12 is equal to 2, correct? Now if I take it for sodium, 23 minus 2 into 11 is equal to 23 minus 22 is equal to 1. So this is definitely not the answer. Next one, if you do 24 minus 2 into 12 is 24 minus 24, so 0. But 23 minus this is 1, so this is also not the answer. Option C, let's check it out. 4 minus 2 into 2 is equal to 0, and then 16 minus 2 into 8 is equal to 0, 2. So option C is the correct answer. Get my point? Yes, clear? Amazing. Another question. See, you will be able to do it. So this is related to the distance of closest approach. Let's check it out. So beam of specific kind of particles of velocity 2.1 into 10 to the power 7 meter per second is catered by a gold nuclei. Z is equal to 79. Find out specific charge by mass of this particle if the distance of the closest approach is this. So R is given to us, my dear student. R is equal to 2.5 into 10 to the power minus 14 meter, right? Yes, we have this, correct. V is also given to us. The V is 2.1 into 10 to the power 7 meter per second. Z is given to us, that is 79, right? Yes, we have to find charge by mass ratio. So at the closest point, when the alpha particle is closest to the nucleus, right, what happens? Initial energy is equal to kinetic energy, right? What do we know? We saw that the initial kinetic energy, right? Initial kinetic energy is equal to the potential energy. So that means that half mv square is equal to 2kze square divided by r. Is that correct? Yes, that's what we know. That's what we know. Am I right? But instead of writing 2kze square divided by r, can I write it to be? Q1 and Q2? Can I write it to be Q1 and Q2 by r? I can, right? I can. This can be equal to, do I have to write 2 now? Do I have to write 2? No, I don't have to write 2. Okay, I don't have to write 2. So what I'll do is, see, I will do K Q1 Q2 by R. Alright, yes, this is the thing. Now what I will do is, check it out. Q1, I know Q2 by M if I do. Okay, Q2 by M will be equal to R V square, yes, divided by, oh, I'm so sorry, here will be a Z also, okay. Yes, what will it be? It will be divided by 2KQ1Z. Am I making a mistake somewhere? Two KZE square. Oh, Q2 also has to be there. You know what, let's do it again. Okay, here is a question for you. Next question. A beam of specific kind of particles of velocity 2.1 into 10 to the power 7 meter per second is scattered by a gold nuclei. Z is equal to 79. You have to find out the specific charge, that is charge by mass of this particle, if the distance of closest approach is 2.5 into 10 to the power minus 14 meter. Alright, okay, so what are the things that we know? Distance of closest approach, that means R is equal to 2.5 into 10 to the power minus 14 meter. Velocity is given to us, velocity is 2.1 into 10 to the power 7, yes. Atomic number is given to us, so Z is equal to 79, it's given to us. We have to find out the specific charge, that is charge by mass ratio, okay. Now we know that at the closest distance, we just saw, no, initial kinetic energy, correct. Initial kinetic energy is equal to P correct, yes. So that means that half mv square is equal to 2kz q1 q2 by r, if you remember, right? Yes. Now what I can do is, I can write it like this also. q2 by m is equal to r q2 by m is equal to rv square divided by 2kzq1. Can I write it like this? I can. Now check it out, what I'm going to do. What is my r? My r is 2.5 into 10 to the power minus 14 m. Alright. What is my v? My v is 2.1 into 10 to the power 7 square divided by 2 into z is 79, k is 9 into 10 to the power 9, and q1 I can write it to be 1.6 into 10 to the power minus 19, correct. Solve this. Once you solve this, once you solve all of this, I think your answer has to be around square 7 to 14, 14 will get cancelled right here, then 19 and 9, 10 will be remaining, 2 into 79 and then 2.5. It has to be around option A. Option A will be the correct answer. If you solve it, great. Option A will be the correct answer. Great. Now my dear students, we are moving towards the best part of the chapter, that is developments that led to the Bohr's atomic model. What really happened that made Bohr reach towards his atomic model? So, you know, there were a lot of data, there were a lot of observed studies that he kept saying about the interactions of radiations with matter and all of that he saw, right? Now, there were two developments that actually played the role, the greatest role in the formulation of atomic model that Bohr made it, right? One was dual character of the electromagnetic radiation, which meant that the radiation can be like a wave or it can be like a particle. Okay. And there were some experimental results regarding the atomic spectra which made him come to the electromagnetic radiation. Now, what is electromagnetic radiation? Well, let's understand. What is electromagnetic radiation? When electrically charged particle moves under acceleration. Write it down. When, I'm so sorry, my handwriting sucks big time. I'm trying to make it better. But anyway, let's write it again, okay? When electrically charged particle, I said, okay? When electrically charged particle moves under acceleration, what happens? Alternating electrical and magnetic field are produced, okay? Alternating electrical and magnetic field are produced and transmitted. Okay, yes. So these fields are transmitted in the form of waves. These fields, how are they transmitted? These fields are transmitted in the form of waves, okay? These fields are, what did I say? Transmitted in the form of waves. In the form of waves called, you got it right, electromagnetic waves or radiation. Yes, called electromagnetic waves. Okay, so basically if I have a, let's say a particle, right, if I have a electrically charged particle and then if I accelerate it, what will happen? There will be some waves that will come out and these are called as your EM waves or electromagnetic radiation. Clear? Now how does it look like? It actually is, now if you see carefully, look at it. So if this is your electric field, this is your magnetic field, both are perpendicular to each other. Yes, both are perpendicular to each other like this, and there is the wave that is traveling in a direction. So all the three of them are actually, once again, remember all of them how they were perpendicular. So like this and like this, correct? Yes, this is how they are all perpendicular, okay? So like this they are all perpendicular to each other, and see, if this is your electric field, then this is your magnetic field, okay? And these two together, this whole 8 thing that you see, this is together your length of the electromagnetic waves, okay? Now let's understand that what actually we saw. The oscillating electric and magnetic field produced by oscillating charged particles, they are perpendicular to each other, which is what I just told you, right? This is what we just told. Now, unlike the sound waves they always, yes, or waves produced in water, you know that sound waves are like a child, they always need a medium, but hey, they don't need a medium, they can also travel in vacuum, okay? Yes, number 3 are that there are many type of electromagnetic radiations and they are different from each other. How? In wavelength. or frequency. Now what are this? We are going to learn in some time. Now these constitute what is called as electromagnetic spectrum. Now because there are different wavelength and different frequency, which is why you are getting different sort of electromagnetic radiations, together when you look at all of them, you are going to get something called as electromagnetic spectrum. What is spectrum? Spectrum is basically from this it started, from that it end, from here it ended. So basically if you take a prism, shine light like this, it will, the light will, you know, scatter into many different colors. That is called as Vibgyor, violet, indigo, blue, green, yellow, orange. So that visible range that you see, the visible range of colors that you see, violet, indigo, blue, green, yellow, orange, red, that is your nothing but spectrum. That's the visible range spectrum. It starts from violet, ends in red. Okay, that's a spectrum. So same thing like that, you also have an electromagnetic spectrum. We're going to read about it, right? And different kinds of units are used to represent electromagnetic radiation. So fourth point is fine. Now let's talk about the properties or the characteristic of electromagnetic wave or electromagnetic radiation. Obviously whenever we talk about something, we need to know about the properties. You know how when a new teacher comes, you always ask, ma'am, or sir, which IIT do you belong to? Sir, how much was your marks? Sir, how many people have you taught? These are what? A teacher's properties, right? The same like that, you are going to ask about the properties of electromagnetic radiation also. Now, I know you have to study more, but learning. So the first one is, let's talk about frequency. What is frequency, my dear student? Okay, let's understand frequency, okay. Frequency is actually the number of oscillations in per second. This doesn't make anything clear, okay. What if, let's say that you have, I give you two biscuit packets, one is Oreo, one is Marie biscuit. Which one would you like to eat more? Everybody together, we love Oreo, right? Great, amazing. Yes, we all love Oreo biscuit, right? Nobody likes Marie. It's only for diabetic patients. That's what we say. Even I used to say this. My parents have diabetes, but I still used to say that. Only you guys eat it. I'm not going to eat it, right? So anyway, everybody likes Oreo. Just for stereotypically we are saying, some of you might be like, ma'am, who said that I like bourbon? Ma'am, who said that I like Good Day? Sure, but just understand, Oreo and Marie, two options. We will all go to Oreo biscuit. Now both the biscuit packets, so I have given you, let's say, two biscuit packets, one Oreo biscuit packet, one Marie biscuit packet. Both of them have 10 biscuits in it, okay? Both of them have 10 biscuits in it. Now what if I give you 5 minutes and I say that finish both of them? 5 minutes you gobbled up the Oreo, you're eating like that, and Marie went in like, can't eat. Now what did I say? I said 5 minutes, how many Oreo biscuit did you eat? 10. You ate 10 Oreo biscuit in 5 minutes, right? 5 minutes, 10 Oreo biscuit. That means in 1 minute you have eaten 2 Oreo biscuits. But when it came to Marie biscuit, you are like, ma'am, I can't eat. So in 5 minutes you have eaten, let's say, 5 biscuits. That means that in 1 minute you have only eaten 1 biscuit. So which one did you eat more? You ate the Oreo biscuit more. So what is the frequency? In 1 minute, how many biscuits did you eat? 1 minute, how many biscuits that you ate is the frequency of eating your biscuits. The frequency of eating Oreo biscuit is 2 in 1 minute. The frequency of eating Marie biscuit is 1 in 1 minute. Same like this, number of oscillations, now not 1 minute, number of oscillations in 1 second. So how many times did the wave, you have seen a wave, right? What is the wave? The wave is usually like this and this and this and this, right? So how many times did the wave come like this and then went like this? Came like this and went like this. So basically this. In 1 second, how many times did this happen? That's your frequency. I messed up my speech big time anyway. So frequency is denoted by nu, and what did I say? It's number of oscillations, yes, in 1 second. Okay. Next comes wavelength. What is wavelength? Wavelength is given by something called as lambda. What is wavelength? Wavelength is basically, see, if I make a wave like this, okay, this, this. The distance between this peak to this peak, the distance between this peak to this peak, this is called as wavelength. So, I can write distance between two consecutive crest. These are called as crest and this is called as trough. Okay. The bottom peaks are called as trough, T-R-O-U-G-H, and this is called as crest. Cool guys. Okay. So, the distance between two consecutive crest or troughs, that's your wavelength. Alright, yes. Now we come to something called as amplitude. What is amplitude? Amplitude, my dear students, look here. This is amplitude. The maximum distance from the rest position. The maximum distance from the rest position or the height of the crest. Okay, let's write it down. What is amplitude? The maximum distance from the rest or mean position, let's say. Okay, mean position is amplitude, or we can also write it as height of crest or depth of trough. Cool, got it. All right, moving on now. Next, what is the next one? Next one is velocity. What is velocity here? Velocity is speed of light. Okay, my dear students, what is velocity? Here the velocity, electromagnetic radiation, they travel in with a velocity of, that is speed of light, 3 into 10 to the power 8 meter per second. Alright, got it? Okay. Now there is something called as wave number. Wave number is nothing but inverse of wavelength. What is it? Inverse of wavelength. बोले तो 1 by lambda. Cool. Alright everybody. Yes. Now what is important is that in vacuum, all types of electromagnetic radiations, okay, regardless of the wavelength, they all travel at the same speed. In vacuum, all of them, they travel in the same speed, and that is your speed of light, 3 into 10 to the power 8 meter per second. Got it? Yes. So here is a formula. What is the formula, my dear students? The formula is, everybody, I am writing it here with blue, that is C is equal to, what is it? C is equal to V into lambda. This is the formula. So C is speed of light, V is velocity, and V is velocity only, no? V is velocity of light, that is C. Sorry, not V, this is frequency. Sorry, this is nu. This is nu, okay, not V. Yes, frequency, wavelength. This is frequency, this is wavelength. And this is speed of light. Cool. So this formula is important. All right. Now moving on, this is how your electromagnetic radiation looks like. Okay. Now what is happening here? See, so this side, what you have is energy is the most here. Okay. At the extreme left side of me, extreme left side here, the energy is the highest. Okay. Energy highest. Okay. And this side, wavelength high. Okay. So basically from this side to this side wavelength increases, and from this side to this side energy increases. Alright, yes, okay. And this is your visible region. So it starts from, actually it starts from cosmic rays, but you can forget cosmic rays because it's not there in your NCERT. You can start with gamma rays, X-rays, ultraviolet, infrared, radio waves, okay. And in radio waves you have radar, TV, FM, all of this, okay. How do you remember it? You can remember it as gamma, XUV, yes, XUV, X-ray, then here there will be ultraviolet also, UV, right, ultraviolet, then visible. So gamma, XUV, infrared, radio, gamma, XUV, infrared, radio, that's how you can remember it. So electromagnetic radiation, till here we have understood. Now let's understand that how do objects behave when they are, when they are introduced to electromagnetic waves. Now there is an object called as black body radiation. I know in the charts you are all going to write Venta black, Venta black, Venta black. I know. So people have started speaking about Venta black and all of these, right? And what is black body radiation, guys? What is black body radiation? Basically, if we have an ideal body, doesn't exist. If we have an ideal body which can emit means produce, it can produce and absorb radiations of all frequency uniformly. Whatever is the frequency, whatever is the number of oscillations, it can emit, it can absorb it, and it can emit them uniformly. That's called as black body. And the radiation that is emitted by, the radiation that is emitted by such a body, such an ideal body, is called as nothing but black body radiation. So a black body is actually in thermal equilibrium with its surroundings. Thermal equilibrium, right, with its surroundings. So the surrounding and this, both of them have the same heat energy, right. It radiates the same amount of energy per unit area, and it absorbs also the same amount of energy from the surrounding at any given point of time. That's what we think, right. Now from here we move towards Planck's quantum theory. What did Planck do? Now Planck said that, you know what guys, forget about all of these, let me explain you something. It can't be just wave that you're talking about, because classical mechanics actually could not explain a lot of things, right. So he came up and he said that he gave the name quantum. What is quantum? Quantum is actually the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. And the energy E of a quantum radiation is actually directly proportional to the frequency, and that's when we say that E is equal to h mu, but that we will come to later. So now understand what he said. He said that different atoms and molecules, they can absorb or they can emit energy in discrete quantities. They are not going to absorb it in waves, they are going to absorb it in discrete quantities, small packets. Just like how you did it with biscuit, right? You can't put the whole biscuit packet in your mouth, right? You took 1 discrete, 2 discrete, 3 discrete. It wasn't like you just opened your mouth and biscuit was just going in continuous wave-like function. No, discrete, 1, 2, exactly, that's what Planck said. So the smallest amount of energy that can be emitted or absorbed in the form of electromagnetic radiation, that is, my dear students, called as your quantum. And he said that the energy of the radiation absorbed or emitted is directly proportional to the frequency of the radiation, which means that basically he said nothing but he said E is equal to what? H and nu is the frequency. What is this H? This H is the Planck's constant. What is it? The H is the Planck's constant. Gotcha? Yes? Okay. So he said that energy of photons. So how do you calculate the energy of photon? Energy of photon is proportional to frequency. E is directly proportional to nu. So if you have to remove the proportionality constant, what will you do? You will write it E is equal to h nu. So the constant of proportionality is called as Planck's constant. Now that h nu you have written, right, h nu. We also know that h nu can be written as hc by lambda, and that's exactly what you have written. So E is equal to hc by lambda. Yes, E is equal to hc by lambda because nu is equal to c by lambda. Remember that formula? This formula, nu is equal to c by lambda. So from here, hc by lambda, we can write it, right? So c is speed of light, lambda is wavelength, and h is Planck's constant. Got it? Yes? Okay. Alright. Now, all of this is done. Now comes another topic called photoelectric effect. What is this photoelectric effect? So in 1887, there was someone called Hertz. H-E-R-T-Z. I'm not liking the blue color anymore, so let me take green color. His name was H-E-R-T-Z, Hertz. In 1887, he performed a beautiful, interesting experiment, okay? And in that, he saw that electrons were being ejected, that is, electrons were coming out when you take certain metal, and when you expose them to a beam of light. You are shining light and you have taken a metal, shining light is hitting the metal and electrons are getting ejected. Electrons are coming out of it, okay? This phenomena was called as photoelectric effect. So let's write it down. Yes, Hertz in 1887 performed an experiment and saw that electrons were ejected when certain metals were exposed to. Okay, exposed to a beam of light, and this phenomena this phenomenon is called as photoelectric effect. Understood everybody? Got it? Clear? Amazing. Now what were the results? What were the results of this experiment? He saw that the electrons were ejected from the metal surface without any lag. There was no lag, as in the moment the light beam hit, electrons ejected. The moment the light beam hit, electrons were ejected. There was not a second of lag between the two incidents. Okay, that's what is written in the first point. Cool. Now it says that the number of electrons that were ejected, it is directly proportional to the intensity or brightness of the light. How bright the light was, on that it depended. Okay. And for each metal, there is a characteristic minimum frequency called as V0, also called as threshold frequency. What is this threshold frequency? So understand this. Let's just say that, okay, so this is my skin, right? I'm going to pinch myself, right? I'm going to pinch myself, I'm going to pinch myself, I'm going to pinch myself. It's not paining, it's not paining, it's not paining. And then suddenly I do this, ooh, it did pain. So when did that sound, ooh, it came, when did it come? When did I produce that sound from my mouth? Not in the beginning. In the beginning I was able to take it. So there was a threshold, there was a point at which I felt like, ooh, this is paining. That is called as threshold. Threshold can be very easily understood in a layman's term as benchmark. Like that's it. After this, I will start reacting in a different manner. Alright. Got it? Okay, so that's your threshold frequency. So there is a frequency below which you will not be able to see the photoelectric effect. You will not see. Only after you have reached the threshold frequency, only after that you will be able to see the photoelectric effect. Okay, got it? So threshold frequency is nu naught and this is your nu. Your frequency has to be higher than the threshold frequency for you to be able to see the photoelectric effect. You get it? Yes? And then the ejected electrons, they come out with kinetic energy. Obviously, bhai, velocity, if there is velocity, there is kinetic energy, right? And the kinetic energy of these electrons, it increases with increase of frequency of the light used. Yeah? Got it? Cool. Now moving on, photoelectric effect. We are continuing photoelectric effect only. The moment I saw the heading, it came in my mind that let's say it again, photoelectric effect. Anyway, so now everybody was, going bonkers about it, that what is this? This is a new thing. We were all talking about wave, and then suddenly somebody comes and no, there is packet of energy. No, this is called as quantum. So then comes Einstein. Einstein was like, "Main batata hu. I will tell you. So everybody was like, sure, go ahead. So Einstein said that the frequency of the incident light, what is incident light? The light that is falling on the metal surface. The light that is falling on the metal surface is your incident light. So the frequency of the incident light is more than the threshold frequency. We understood. And the excess energy, h nu minus h nu naught, is imparted to the electron as kinetic energy. Understand this. So if I have let's say this is a box. Okay, this is a box. Correct? What did I say? I said that the frequency of the incident light. So this is the frequency of the incident light. The frequency has to be nu. This body has a threshold frequency nu naught, right? So when this nu hit the box here, what happened? Some amount got absorbed. Some amount of it got absorbed, right? But the rest of it was transferred. So some amount of it got absorbed, and from here the electron came out. What did this electron have? This electron had nu minus nu naught. Still did not get it? Let's understand it one more time. Let's say that you are giving 10. Okay? 10 is the energy. 10 is the energy with which the incident light is coming and falling on the metal surface. And let's just say that the threshold frequency is 5. The threshold frequency is 5. 10 is the frequency with which the light is falling on the metal surface. 5 is the threshold frequency. So what will this? The electron will come out with 5. The electron will have a kinetic energy of 5 because 10 minus 5 is also equal to 5. No? Got it? 10 minus 5 is equal to 5. That's what he said. So how can we write it? So the kinetic energy, that means the kinetic energy, what did I say? The kinetic energy is basically nu minus nu naught. If I write it properly, I can write it as half mv square is actually equal to, see, I have to, remove the proportionality constant and everything. So it will become h nu minus h nu naught. Or h nu, if I have to find what is the frequency, I can always calculate it as h nu is equal to h nu naught minus half mv square, not minus, sorry, plus half mv square. So this is a formula that is important for us. Got it? Yes? Right, everybody? Understood, everyone? I can also write it as, check it out here, h nu. So can I not write it as hc by lambda is equal to hc by lambda naught. I can also write it as hc by lambda naught plus what? Ke plus Ke, right? I can write it like this, correct? Absolutely right. Absolutely right. Yes, absolutely right. Okay, got it, everybody? Understood this? Amazing. All right. Now, what do we have to do? So this lambda naught is now if I have to find it out, okay, let me write it down. So lambda naught is basically the threshold wavelength. This is the threshold wavelength. Cool. And what is lambda? Lambda is the wavelength of the incident light. Easy peasy biryani tasty. Wavelength of the incident light. Cool hai? Yes? Okay. V is the frequency of the light. V, sorry, not V again. Nu is the frequency of the light. Nu naught is the frequency of the nu naught is the threshold frequency, right? So everything all is clear. All right, all is clear. Now, my dear student, let's take a look at the graphs of the photoelectric effect. Let's do that. Yeah, let's do that. Chalo. This, right? H nu. Yes, H nu is equal to H naught plus H nu naught plus half mv square. What is the formula? The formula that we got here is H nu is equal to H nu naught plus half mv square, which means nothing but K, kinetic energy. Is that right? Is that what we got? Correct. Half mv square is kinetic energy. So that means that I can also write Ke is equal to H nu naught. Yes, not H nu naught, it will be H nu minus H nu naught, correct? Check it out. H nu minus H nu naught, am I right? Now this formula Ke is equal to H nu minus H nu naught, don't you think that it looks like Y is equal to mx minus c? Absolutely, yes. It looks like Y is equal to mx minus c, right, everybody? So let's take a look at the first graph now. All right, yeah. So let's do number 1, graph number 1, where I'm going to draw a straight line like this, a straight line like this. These are my x's, yes. So this one, let's draw it kinetic energy. Yep, kinetic energy. And what will this be? This will be nu. Obviously, this will be nu. Okay. So y is equal to mx minus c, right? Y is equal to mx minus c. So the first graph is between kinetic energy and nu, that is frequency. Okay. So my graph will be somewhat like this. This will be my first graph. Okay. Yes. Now let's do a second graph. Our second graph will be between number of ejected electron and frequency. What did I say? It will be between number of ejected electrons versus nu. Okay. So how will this graph look like? Now this graph will look a little bit like, take a look at it. It will be like this. Sorry, my hands are only not straight. How will I ever be able to draw a straight line? So like this, yes, where nu is here and this is my number of electrons. Okay, this will be like this. This is the graph that I will get. Okay, all right. Now let's do another third graph. My third graph is number of ejected electron versus intensity this time. Okay, no more frequency. Let's do intensity. So number of ejected electrons versus intensity. If I draw a graph for intensity, what will I get this time? This time my graph will look a little like how? Any idea? This time is going to be like this. Yes, because as you increase the intensity, the number of ejected electrons also increases. So this is my intensity. All right. And this is my number of electrons ejected. Okay. Now, are we going to end it at third? No, we are going to do another one. Yeah. This time we are going to do another one. Okay. This time, what if I change it? My fourth graph is now, look here. My fourth graph is between, see, this was kinetic energy versus nu. This time let's take nu versus kinetic energy. Okay. If that is the case, then my graph will look a little like this and then this. Yes. So this is where I am taking Ke and this is where I am taking nu. Now what will happen? Take a look at this. So Ke is equal to h nu minus h naught, right? That's what I wrote. Yes, that's what I wrote. But what if I want to again write it like this? Like this. Yes. What if I write it as h Ke is equal to, what will be Ke is equal to? Chalo, let's write it here, okay? With a different color, huh? So Ke, from that formula, I can write Ke is h nu minus h nu naught. Is that right? That's the formula, right? That's the formula. So I can also write it as h nu is equal to h nu naught plus Ke, correct? Yes? Yes, everybody? Right. Now what if, just take a look at it, what if I divide it by h on both the sides? If I divide it by h on both the sides, then my equation becomes nu is equal to nu naught plus 1 by h Ke. Am I right? Yes. And that means that my graph will be somewhat like this, where the slope will be equal to 1 by h. You getting my point? Yes. And this part will give you nu naught. Got my point? Yes. So these are the 4 graphs that you have to remember. Okay, these are the 4 graphs that you have to remember. Now we come to something called as stopping potential. So what is this stopping potential? Any idea? What is the stopping potential, guys? Just a second. Where is my cursor? Yeah. What is the stopping potential? What do you guys think? Actually, just a second. Okay. So basically the stopping potential is the potential that is required from stopping the electrons being ejected. You getting my point? Okay, now comes a topic called as stopping potential. What is stopping potential? Stopping potential is basically the minimum amount of potential that is required to what? That is required to stop the photoelectric effect. What did I say? The minimum potential required to stop the photoelectric effect. Okay, let's write it down. To stop the photoelectric effect is called as stopping potential. All right, everybody? Yes? Okay, so now of course there will be a formula here also. What do you think? Won't be there a formula? There will be. Yes? What is the formula? So take a look at it. Of course, we will write it as Ke is equal to, yes, Ke is equal to Q into V naught. We know that, right? K is equal to Q into V naught. Once again I said V naught, it's nu naught. Yes, that means that kinetic energy is equal to E into V naught. Okay, all right. Yes, is that what you get it? So this is our minimum potential that must be applied to stop the photoelectric effect. Clear? This is something that you have to remember. Alright. Moving on from here, we have a question. So in photoelectric effect, the kinetic energy of photoelectrons increases linearly with wavelength of incident light, frequency of incident light, velocity of incident light, or atomic mass of an element. We just did it, guys. We just did it. Yeah, we just did it. Kinetic energy of photoelectrons increases linearly with, what is the answer? Of course, option B, frequency of incident light. Very good. Next question. Electromagnetic radiation with maximum wavelength is, do you remember gamma, XUV, infrared, radio wave. So what is it going to be? And what happened was, this side energy was extreme, that side wavelength was extreme, right? So radio wave is the one that has the maximum wavelength. Don't forget it. Okay, next question. Okay, so electromagnetic radiation having lambda is equal to 310 angstrom. 10 angstrom is subjected to a metal sheet having work function 12.8 electron volt. What will be the velocity of photoelectrons having maximum kinetic energy? Okay guys, so what is it that we know? We know that E is equal to H nu, yes, H nu, yes, and we also know that this is equal to Hc by lambda, am I right? We know that. Yeah, now what is H? H is equal to 6 point, what is it? 6.63. 6.63 into 10 to the power minus 34. Right, that's our H, correct? Okay, C and all of that you know, correct? All of that we know. Now kinetic energy, so maximum kinetic energy, right? Maximum kinetic energy, right? So Ke, so Ke will be what? Ke, we all know that it is half mv square, half mv square, yes, yes, and that half mv square is basically equal to the H nu, which is basically equal to W. W is basically the work done, okay. Half mv square is equal to H nu is equal to W. W is basically 12.8 EV, that's given to us. 12.8 electron volt, that is given to us, okay, alright. Now once again we know that Hc by lambda it is, so E is equal to 6.63 into 10 to the power minus 34 divided by Hc lambda, guys, Hc. So this multiplied with 3 into 10 to the power 8 meter per second, am I right? Yes, this is what you will do. Yes, and divided by what is my lambda? Lambda is given to us, see, 310 angstrom, okay. So let's write it, 310 into 10 to the power what? Minus 10, because it's angstrom, correcto? Yes. So this will be all equal to, I think, around 10, 8, this 310, 3, okay. What will this be equal to? What will this be equal to? Any idea? Any idea? No? Chalo, forget it. This you can calculate later, okay? This you can, I think, calculate later. You do this calculation, okay? Alright, so once you have done all the calculation, then we also see that W is equal to 12.8 EV that is given to us, right? So instead of that, what if we change it into joule? If we change it into joule, then it will be 12.8 EV multiplied with 1.6 into 10 to the power minus 19. Alright, yes, 12.8 electron volt multiplied with 1.6 into 10 to the power minus 19. Now minus 19, once we do this, the resultant will be in joule, okay, the resultant will be in joule, got it? Yes, alright. So that means that you will get it around 12.8 into 1.6, that means it will be around 2 point something will be the answer, okay. Now once again, if I do half mv square is equal to H nu minus W, yes, correct everybody. Now you know what is your W, You know what is your W, right? Correct, everybody? Great. You know what is your E? What is your E? E is something that you have calculated from here. Yes, from here. Got it? Yeah, you would have calculated it from here. And then M, you know, is around 9.1 into 10 to the power minus 31 kg. Correct? Now, when you put all of these, you will get V square. You will get V square, okay? Whatever you get as V square, then what you have to do is V is equal to root over this, okay? Alright, that is what you have to do. Please calculate it on your own. I don't have a calculator. I don't want to use the calculator, but you can do this much, okay? You can do this much. I'm pretty sure about it. Alright guys, so I think the correct answer is option C. They're saying the correct answer is option C. So what you can do is you can just go back, calculate it and then check it out. Alright. Now we come to something that is called as Bohr's atomic model. This is the beginning of our many derivations that we are going to do now, okay. So Bohr's model of the atom was actually another stepping stone for us, right? Yes, after Rutherford, this was another stepping stone. So Bohr's model of the atom, it was proposed by no one else but Niels Bohr, right, in 1930. Because obviously there were drawbacks that were related to Rutherford's model, and Niels Bohr just wanted to explain the things a little better, right? So he was the first one who could explain quantitatively the general factors of the structure. Of what? Hydrogen atom, my dear students. Please do remember it that Bohr's atomic model is great, but for hydrogen only. For one electron system it is great, but not for something else, which is why we came up with something else later on, right? So for hydrogen atom and its spectrum, and he used Planck's concept of quantization of energy. Now see what magic he has created, okay, what magic he has created. So what he said was, the electrons in the atom can actually move around the nucleus. We all know that, absolutely right, we know that the electrons in the atom can move around the nucleus in a circular path of fixed radius and energy. Yeah, absolutely bro, we know that. Great. These paths, they are called orbits. He spoke about orbits now. Stationary states or allowed energy states. So what are the names that you can call them with? What are the names, guys? The names are, check it out. The names are, yes, these paths are called orbits, stationary states or allowed energy states. Yes. Now these orbits are arranged concentrically around the nucleus. You understand what is concentric? This is your nucleus. This is your nucleus. This. One after another. That's called as concentric circles. Got it. Yes, this is called as concentric circles. Alright, yes, we understand this. Now, moving on from here, now comes the postulates. That means things that he typically or particularly said. So he said that electron revolves around the nucleus due to the centripetal force that is provided by the electrostatic force of attraction. You remember, nucleus has positive charge, electrons are negatively charged. There is a force of attraction. Electrostatic force of attraction is there, and because of this electrostatic force of attraction, they have a centripetal force which governs the movement of the electrons. Great. Understand? Amazing. Yes, got it. Now, if this is a centripetal force, check it out. Yes, what he said is, if this is our nucleus, and if this is an electron, then the electron is being pulled here. The electron is being pulled here by who? By the centripetal force. By the centripetal force, the electron is being pulled, correct? But just equivalent to that, there is also a centrifugal force. So the centripetal force is the electrostatic force, that means Coulombic force. This is equal to a Coulombic force because it's an electrostatic force. But this centrifugal force, that is the kinetic energy of the electron, right? Are you getting it? So this is, my dear student, that K, Q1, Q2 divided by R, and this, my dear student, is half mv square. Both of them are equal. Getting my point? Anyway, we are coming to it. Now he said that energy is emitted or absorbed. Listen to this very carefully. He said that. What Rutherford said, that electrons are revolving, they are emitting energy, and then finally at certain point they have lost all energy and they fall into the nucleus, and we are questioning the existence of matter now. But Niels Bohr said something very brilliant. He said that, hey, the electrons are moving around the nucleus, no doubt about it, but is it emitting energy? No. When it is moving or when it is revolving around its particular orbit, there is no energy emission that is happening. The energy emission, my dear student, is only happening when the electron jumps from a lower level to the higher level or from higher level to the lower level. That's when energy gets emitted or absorbed. Yep, that's what he said, and that changed the way we look at all of these things. So he said that the energy, okay, from E2 is this to this, right? This to this. This is your E2 minus E1. So in first energy level, let's say it's E2. In the second one, it's E1. So E2 minus E1 or delta E, the difference in the energy is basically nothing but h nu or is equal to hc by lambda. Make sense? Only those orbits are permitted, he said. Only those orbits are permitted in which the angular momentum of the electron is a whole number multiple of h by 2 pi. Okay? What did he say? He said that mvr is equal to nh by 2 pi, where n is equal to 1, 2, 3, etc. Achha, this h by 2 pi, no, this h by 2 pi can also be written as h bar, okay. What can you write it as? H bar. So you can write it like this also, that mvr is equal to nh bar, okay. And this means that like energy, angular momentum of the electron in the atom is also quantized. The angular momentum is also quantized, not just energy, but angular momentum is also quantized. Now let's derive this whole thing, okay. So according to Bohr's postulate, we have understood that, please take a look at it, my dear students. Yeah, please take a look at it. I'm going to do this here. So according to Bohr's postulate, we understand that centripetal force is equal to Coulombic force, which is equal to centrifugal force, right? Now to start with, we have mv square by r is equal to k z e square divided by r square. Correcto? Great. Alright. So what we can cut? Now from here, what we can cut is, take a look at it, we can cut this, we can cut one of the r. So that means that our mv square is equal to kze square by r, righto? Yes. That means that r can be written as kze square divided by mv square. Am I right? And let's call this equation to be number 1 or equation 1. Alright? Yes. Now my dear students, okay, now from Bohr's postulate we know that mvr is equal to n dot h by 2 pi. Am I correct? Yes, we know. So how can we find the velocity? Very easily. So v is equal to nh 2 pi r m. Is that right? Yes, right. Now let's substitute this value. Okay, let's write it here. Substitute in equation 1. Substitute in 1. What was our 1? 1 is r is equal to kze square divided by mv square. Okay, kze square divided by mv square, right? That is our r. If we substitute this in equation 1. Okay, let's do it. Yes, let's do it everybody. Substituting in equation 1, what will we get is this, right? R is equal to kze square. So let's take it here. Let's take it here. Let's take mv square r. So let's imagine that it is mv square r is equal to kze square, correct? So that means if I put the value of v square here, that means nh2 pi r m square r is equal to kze square. Right to everyone? Make sense? Nonsense? Makes sense, right? Now what I can do is I can also write it as n square h square, 1m gone here, from here also 1m will go. That means it will be 2 pi, sorry, not 2 pi, it will be 4 pi now. Square, right? Here see it is square. So that means it will be 4 pi. So it will be 4 pi r square, yes, 4 pi square r square m. Makes sense? This is equal to r, r will also be here, r will also be here, right? R will also be here, or r gets cancelled. Oh, r gets cancelled, r gets cancelled, r gets cancelled. So this will be equal to k z e square. This is nothing but it's equal to, see here, n square h square divided by 4 pi square m r is equal to k z e square. Make sense, everybody? Getting my point? Getting it, everyone? Amazing. So now from here what I can see is if I cross multiply, then what will be my r? What will be my r? From here I am taking it here. Yes, I don't want to bend too much and write it, okay? So check it out. So my r will be equal to, what will be my r equal to? My r will be equal to n square h square divided by k z e square pi square m and 4, yes, is that right? 4 k z e square pi square m. This is the formula for radius. What is this? This is the formula for radius, okay? Do not make a mistake here. Please do keep writing it down while I am writing it, everybody. While I am writing it, please do keep it. One second, where is my cursor again? Yeah, this is where. Found it. Okay. Now what we can do is, now check it out. Now what we can do is, let's put the values, okay? Let's put some values here. Let's put m is equal to 9.1 into 10 to the power minus 31 kg. Correct. Yes. What is h? H is Planck's constant. You know that also. H is equal to what? 6.626 into 10 to the power minus 34. Yes. Yes. Very good. Pi, forget about it. K is 9 into 10 to the power 9. Yes. K is equal to 9 into 10 to the power 9. Yes, everybody. And what is E? E is equal to 1.6 into 10 to the power minus 19. Am I right? Yes. If you put all of these values in this, you know what you will get? You will get R is equal to, there is a number. Please do remember the number. The number is 52.9. What is the number? 52.9. So only keeping the variables here, 52.9 into n square divided by, what will you keep? Atomic number Z in picometer. Okay. After all of these, you will get this value into picometer. So please remember this. If you want to solve problems directly, you have to remember this. You can also remember this derivation if you want to. It will be great for your JEE advanced level. Coolio. All right. Now once again, everybody, let's move forward. Okay, let's move forward. I had to, I think, write it here also, but chalo, koi baat nahi. I think you get it, right? I think you get it. Okay. Chalo. Now let's do it. From Bohr's postulates, once again, what do we know? mvr is equal to nh2 pi, right? Okay, got it? And we also know now that R is equal to n square h square divided by, what is it? N square h square 4 pi square k z e square m, right? This is our R. Correct? Yes. So let's keep this to be equation 1, and if we keep this to be equation 2, what will we get now? If we put the value of r in equation 1, let's put r in equation 1. If we put the value of r in equation 1, do you know what we will get? We will get velocity. We will get velocity. But let's do it. Okay, what is our r? Okay, so we have m, v, and r is, my dear student, let's write it in a bracket so that we don't get confused. N square, h square, 4 pi square, m, k, z, e square. Am I right? This is our r. Yes. Is equal to n dot h by 2 pi. So h cancel, n cancel, 2 cancel, 2 here remaining, pi 1 cancel, right? So this side only k is remaining, that means that mv, in fact m cancel, here 1 m cancel, okay? So this will be equal to v n h divided by 2 pi k z e square is equal to k, correct? But this I can change it this side. So v will be equal to k square 2 pi k square z e square divided by nh. Make sense? Make sense? So this is your velocity formula. This is your velocity formula. Get my point, guys? This is my velocity formula. Okay? Alright. So putting the value of ke, now what you can do is, if you put the value of ke and h, you know what is k? 9 into 10 to the power 9. You know what is e? 1.6 into 10 to the power minus 19. You know what is h? 6.626 into 10 to the power minus 34. If you put all of that, you will get a velocity constant value, that is 2.18 into 10 to the power 6 z divided by 9. Only variable thing is z and n. Z and n are the only variable, and here you will get velocity in meter per second. Here you will get velocity in meter per second. Got it? Got it? Got it? Got it? Got it? This makes sense, right? This makes sense, right, everybody? Great. Okay now. Okay now. Moving on from here. Moving on from here. Do we also want to find out the energy, guys? I think so. I think so. Right? We do. Okay. Okay. Now let's do it for energy. Okay, let's do it for energy. Let's find out the energy. So how will we figure it out? So total energy of an electron that is revolving in a what? In a particular orbit, guys. Yeah. So let's write it down, that total energy of a particular electron, of an electron, let's write, yeah, what particular and all, why make it long, of an electron revolving in a particular orbit. Now let's write particular, in a particular orbit, because there are a lot of orbits, correct? In a particular orbit is, what is it? We know that total energy is equal to definitely kinetic energy plus potential energy. Correct too? Great. What is kinetic energy? Half mv square. What is kinetic energy? Half mv square. Right? But now we know that from Bohr's postulate, what do we know? mv square by r is equal to kze square divided by r square. Remember that? Yes, absolutely. Yes, we don't remember it. mv square by r, mistake happened here. mv square by r, yes, mv square by r is equal to k z e square divided by r square only, no? R square, okay. So what will we get? We will get r will cancel, we will cancel. So what will we get here? So mv square is equal to kze square. That means we know that mv square is equal to kze square by r, correct? That this value, don't you think that this value we can put it in this equation? Correct? We can do this? Yes. we can put this value in this equation. Yeah. So what we will get? Our kinetic energy will be equal to, check it out, will be equal to K Z E square by 2R. Make sense, nonsense? Yes, no? Yes, great. Okay, this we understood. Now what about potential energy? That also we will have to figure it out, na Baba? Yes. So how do we calculate our potential energy? Chalo, let's check that out as well. Okay. Now what is our potential energy? Our potential energy, as far as we know that potential energy is always equal to minus half of Ke, right? Potential energy is always minus half of K. Potential energy is this, minus KZE square divided by R. Okay, alright, yes. So our total energy becomes, okay, total energy, we already know that what happens is potential energy is equal to minus half of, let me just write it down here, okay, PE is equal to minus half of K. Alright, this is what we know. Because we know this, so we can write directly that PE is equal to, not minus, it wasn't minus, I think it was twice, yes, I think I made a calculation error just now, just a minute. Yes, absolutely yes. What I did was, because this is 2R, right, this is our K, so it cannot be minus half, it has to be, just a minute, it has to be minus 2K. So if I put 2 into this, then the 2 gets cancelled, right? Yeah. So PE will become minus KZE square divided by R. Okay, alright, PE will become minus KZE square divided by R. So my total energy will be KE, this part is my kinetic energy, plus, even if I write plus here, this is still minus, so minus KZE square divided by R, that is minus PE. Yes. Now, you might be thinking that, ma'am, how does this happen? What is our KE, guys? Check it out. What is our KE? Our KE is KZE square divided by 2R minus KZE square divided by R. So, if I take the LCM, my LCM will be 2R. So, this will be KZE square minus, now 2 will get multiplied here. So, 2 KZE square. Now, if I minus it, then what will I get? I will get minus KZE square divided by 2R. Make sense? See, this is exactly what you are getting here. Right? This is exactly what you are getting here. Got it? Yes. Now we know that R is equal to what? Now we know that R is equal to N square H square divided by 4 pi square M K Z E square. This is our R. So if I put that, okay, now if I put the value of R in our TE here, yes, if I put the value of R in this case, then what will I get? Check it out. Minus K Z E square divided by 2 into N square H square divided by 4 pi square M K Z E square. This, yes, which means that this is equal to, all of these will go up here now, but just this gets cancelled here, okay. So it will be minus K square Z square e to the power 4, yes, then it will be pi square, here will be a 2 divided by N square H square, and that is your total energy. This is your total energy. Remember this as well. This is also a value that you will have to remember. Cool? Yes. So from all of these here, okay, I was right only. Oh no, yeah, I was right. Yeah, see, Ke plus P, yes, so minus Ke is equal to half of P, yes, and Pe is equal to, potential energy is equal to minus of 2 Ke, and Te is always equal to, total energy is equal to minus of kinetic energy. Alright, these are the things that you know. Now, energy of electron in Bohr's orbit, it continues a little bit more, it continues a little bit more, it doesn't get ended here only. So, let's take a look at this also, yeah. Now, if I put the value of, so total energy you saw, let me write down that formula again, right? Let me write down that formula. So, we know that total energy is equal to, it's a huge formula here, see, minus 2, what is it? K square Z square e to the power 4, okay? K square e to the power 4 Z square, then pi square divided by n square h square, correct? This is your formula. So now if you put the values of K, E and H, right? If you put all of these value, now we will once again get a constant formula where total energy is equal to, my dear student, minus 13.6, and what are the variables? Z and N. So it will be minus 13.6 into Z square by N square. This will be in what will be the value? So what will be the unit? It will be electron volt per atom. This is also something that we will have to remember. Great. Understanding, everybody? Yes. So this is the formula sheet that I have given. These are the things that you have to remember for your calculations. This is the total energy, minus 13.6 Z square by N square electron volt per atom. Potential energy is 27.2 Z square by N square eV per atom. Kinetic energy is once again 13.6. See, this is minus 13, this is 13.6 Z square by N square. Radius of nth Bohr atom. In the exam, whatever they give you, 1, yes, first, second, third, fourth, you will be able to calculate it with this formula. Rn is equal to 0.52 n. What is n? N is this number. Yes, n square divided by z in angstrom, you will get it. Velocity of the electron in nth orbit. These are the things that you should print it out and keep it in front of your table and remember it every single day. I'll give you the PDF in the Telegram channel. Please do join the Telegram channel so that you get the PDF. And then you will not have to study at all. You also have the energy 1, energy 2, energy 3, energy 4, energy 5. All of this I have given to you, okay. Now let me take a break and let me drink some water. Whew. You should also drink some water. Drink it up. All right. Okay. So, now moving on from here, there were certain bit of limitations. Nothing in the world comes without limitations. There were certain bit of limitations. The limitation was that he could not explain the line spectra of atoms which contain more than one electron. So Bohr's model of atom is very limited to one electron system. Okay, it's very limited to one electron system, that is Na10 plus H hydrogen, right? Basically anything that looks like hydrogen, Li2 plus, is where it is limited. Okay. Next is that he could not explain the presence of multispectral lines. He could not, right? Bohr could not explain the de Broglie concept of dual nature of matter. So all this time Einstein said that, let me tell you, it is particles, yes. Before that everybody was like wave, and then de Broglie came and he said that no, it's dual. It can behave like a wave, it can behave like a particle. Yeah. So Bohr could not explain the splitting of spectral lines in the presence of electrical field, Stark effect and magnetic fields, Zeeman effect. This also I'll write it down for you and I'll explain it. He could not explain Heisenberg's uncertainty principle. So that means from all of these we understood that we have to read now de Broglie, we have to read Stark effect, Zeeman effect, and we have to read Heisenberg's uncertainty principle. Now coming to hydrogen spectrum, okay, what is this hydrogen spectrum? Understand this, that the line spectrum of hydrogen atom was observed by Balmer, and that's why the first spectral line that you see in your NCERT is what? Balmer, yes, Lyman, Balmer, Paschen, bracket, fund, all of that you see, right? But the first one was actually observed by Balmer first. Okay, Balmer observed it in 1885. And he saw that hydrogen gas at a very low pressure taken in a discharge tube, yes, and the light emitted on passing the electric discharge is examined with a spectroscope. The spectrum that is obtained is called as emission spectrum of hydrogen. Now here you see there are two spectrums, right? You must be thinking that, ma'am, what is this? What is this? So this is hydrogen absorption spectrum, and this is what is called as emission spectrum. Emission is something that is emitted, that is given out, and absorption is all the things that is absorbed by it. Now take a look. This absorption and the emission spectrum, do you see any similarity? There is. If you look carefully, there is. All the places where you see there is black is where you get to see a light here in the emission. See, black and light here, black and light here, black and light here. That means that the absorption spectra and the emission spectra, these are complementary. Yes, these are complementary. So if this happens, this will also happen. If this happens, this will also happen. So whatever is absorbed, understand this. So wherever you see black is actually the wavelength that was absorbed by hydrogen. And here what you see are the emitted spectra. So what Balmer saw was emission. Yes, what Balmer saw was emission. So basically what he did was, he took a tube where there was hydrogen gas, and there was a lens, right, just the normal lens that you use in your, the concave lens, basically, the concave lens that you use in your physics laboratory. Then there was a very thin, a thin narrow slit was there. You remember in physics you will do this experiment called as Young's modulus later on, but anyway, so very thin narrow slit is here, and then from here when the light has passed through another lens and then through another prism, you see the emission spectra. Okay, you see the emission spectra. Cool guys, cool. Yeah, all right. Now you see that there is Lyman spectra, there is Balmer spectra. So what Balmer saw, did you just notice that there were different colors? There was violet, there was indigo, there was blue, there was blue here again, and then there was red also. So these were the lines that Balmer saw, right? So Balmer saw something that is in visible spectra. Lyman saw something in ultraviolet spectra. Paschen saw something is infrared. After Paschen there were another two, right? Fund and Brackett, and then there was another one called as Humphrey. Okay, Humphrey you don't have to study though, it's not there in your book, right? So you will only study from Lyman, Balmer, Paschen, Fund, Brackett. Okay, these are the ones. Lyman saw in ultraviolet, Balmer saw in visible, Paschen saw in infrared, Fund was also in infrared, Brackett also saw it in infrared, and Humphrey was in far infrared. Yes, far infrared, that's what he saw. Okay. Now what happens is, there is something called as Rydberg's equation. This is one equation that you have to remember. Even if you forget your name, even if you forget your JEE roll number, but please don't forget this, because from here questions definitely do come. Okay. So 109677 into Z square. Z, you know what is Z? Z is the atomic number. N1 square, what is N1? N1 is N1 square, N2 square. Yes. So when electron jump from N2 to N1, see, from N2 to N1, it is Lyman series. Yes. When it comes from, okay, this is where we have made a mistake here, N2 to N1. Everywhere it is written as, okay. So when the jump is only 1, right, when the jump is always to 1, yes, it is called as Lyman series. When the jump is always at 2, n is equal to 2, see, do you see n is equal to 2? It is Balmer series. When the jump is always n is equal to 3, it is Paschen series. After that it is Brackett, and after that it is Fund. Okay. So I said it Fund Brackett, it is Brackett Fund. Okay. It's Brackett Fund. Got it everybody? Yes. Now once again guys, from Bohr's postulate we have to do another what? We have to do another solving. Okay. Let's do it guys. Let's do it. Array. 1 second. This is why. So once again from Bohr's postulate, we know that delta is equal to E2 minus E1 which is equal to h nu is equal to hc by lambda, correct? Now we also know that hc by lambda is equal to E2 minus E1 which is equal to minus 2.18 into 10 to the power minus 18 z square by n square, n2 square minus this. So basically this is what is given to you, right? Now from here, okay, from here, please check it out, yes, this is what is given to you. Now from here what we will do, listen, I hope you are all focusing here, okay, I hope you are all focusing here. So from here what we can do is red, yeah, keeps happening. Anyway, where was I? hc by lambda is equal to E2 minus E1, yeah. So hc by lambda is equal to E2 minus E1 is equal to minus 2.18 into 10 to the power minus 19, correct? But do I also see that this is also minus 2.18 into 10 to the power minus 19, this is also minus 2.18 into 10 to the power minus 19. Now don't you think that I can also take z square here as common, z square also if I take it as common, yes. Now what I can do is, check it out, I can do 1 by n1 square because this is minus, so plus, yes, then minus because here is a minus sign, so what I can do is 1 by n2 square. Makes sense, nonsense? Makes sense? One more thing that I can do is, see, I can also write it as 1 by lambda is equal to, if you remember, it is nu bar which is equal to, what will it be? Check it out, 2.18 into 10 to the power minus 18 divided by hc can be taken here, right? I can take the hc here because I was trying to find 1 by lambda. This multiplied with z square, obviously, because z square is here, z square, then 1 by n1 square minus 1 by n2 square. Make sense? Make sense, everybody? Great. Now what I can write it as 1 by lambda is equal to nu bar equal to this whole part. Do you see this is constant, this number is constant? So that means that I can write that to be RH, which is nothing but this, which is nothing but Rydberg's constant, yes. So RH into z square divided by 1 n1 square minus 1 by n2 square, and this is nothing but your Rydberg's constant, which is, chalo, let's write it down here. One zero nine 109,677. Got it? Yes, that's it. We are done with this. Okay. Now, just remember that this is something that you can remember. If n1 is 1, yes, the bottom line is 1, and then n2 can be 2, 3, 4, right? For Balmer, it is 2, always in the second line. So 3, 4, 5. Balmer is invisible. Paschen is 3, 4, 5, 6, infrared. Bracket is also infrared. Fund is also infrared. Achha, one more thing, did you notice that right here, it has a lot of gap. But then as you go up, the gap is reducing and reducing and reducing. Do you know why? Because right here, the energy gap is a lot. Yeah. But at this place, the energy gap is less, and as you go up in the infrared region, the energy gap goes on reducing. Okay. Now, do you want to find out that these are, see so many lines are there, right? 1, 2, 3, 4. 1, 2, 3, 4, 5. There are 5 lines here. Here there are only 1, 2, 3 lines. How can we remember how many lines are there? So the total number of spectral lines, you can find it with a formula, and the formula is delta n, that again in bracket delta n plus 1 divided by 2. And what is delta n? N2 minus n1. Whatever is your n2, just subtract that from n1. For Lyman, your N1 will be always 1, right? For bracket, your for Balmer, your N1 will be always 2, okay? So the total number of spectral line during any transition means the number of maximum possible spectral lines if an electron makes a transition from one energy state to another energy state. Got it? Now coming to Zeeman effect and Stark effect. What is Zeeman effect and Stark effect? As we know that, just see, take a look at it, okay? Man, right? It's written here man. So from man we can remember that the splitting of spectral lines, from here we can remember that the splitting of spectral line in magnetic field. Got it? And Stark, who can we remember when we say Stark? Do you remember Robert Downey Jr., Mr. Stark, Avenger? Yeah. So Stark, he used to do a lot of electronics things and stuff, right? So we can remember that the splitting of that's it. All right. Now we come to de Broglie. So what did de Broglie say? De Broglie basically said that according to him, the wavelength of a moving particle of mass m with velocity nu is given by lambda is equal to h by mv. What is mv? mv can also be written as, see, mv is equal to p. What is p? P is momentum. What is this? This is momentum. M is mass, V is obviously velocity. Yes, yes, V is obviously velocity. So what is rho? See, M is mass of the particle, V is velocity, and P is momentum. Correct? P is momentum. That's what he said. Now de Broglie says that according to de Broglie, the circumstances of the nth orbit is equal to n times the wavelength of electron. So basically, see, if n is equal to 3, there are 3 waves. Do you see? If n is equal to 4, there are 4 waves. Do you see? If n is equal to 5, do you see there are 1, 2, 3, 4, 5, 5 waves. If n is equal to 6, then 1, 2, 3, 4, 5, 6, 6 waves. Gotcha his point? It looks very complicated, nothing much, okay. All he said that circumference of the nth orbit is equal to n times the wavelength of the electron. So basically circumference is what? 2 pi r is equal to n lambda. That's all he said. 2 pi r is equal to n lambda. That's all. Now let's find out the relationship between wavelength and kinetic energy. So lambda is equal to h by mv. We know that. You know that. I know that. Correct? Yes. This is, let's say, equation 1. Now my Ke, kinetic energy, is equal to obviously half mv square. Let's call this equation number 2. Works? Works. What let's do is, now let's square the equation 1. If you square the equation 1, you will get lambda square is equal to h square by mv square. Am I right? Yes? Mv square as in this, right? H square by mv square. So that means that mv square, actually it is m square v square. Actually it is m square v square, but let me not write that. Let me write here mv square, okay? So if I write mv square, so mv square will be equal to, let's say that h square divided by lambda square and m, right? Now let's call this equation to be 3. Okay, all right. Now what do I have? I have Ke is equal to half mv square, so I can write 1 by h square divided by lambda square m, which is nothing but, am I right? This is my Ke. This is my K. Right. Oh, what did I do? I had to write half mv square. Oopsie daisy. Honest mistake, guys, honest mistake. See, one thing you make a mistake and the whole thing goes for a toss. Anyway, it has to be, just a minute. So K is equal to half mv square, right? So we'll write half and then h square by lambda square m. Correct? This is our K, right? This is our K. This means that I can also write lambda square is equal to, if I take lambda here, then my lambda square will be equal to h square by 2m ke. Yeah. So lambda square will be equal to h square divided by 2m k. Yes. So that means that my lambda will be equal to root over h square divided by 2m dot k. Yes. And that is the relationship between wavelength and kinetic energy. Okay, so let's start with the first one. The first one was, obviously we wrote it here somewhere. This lambda is equal to h by p. Okay, lambda is equal to h by p. Let's write it down here. Number one is lambda is equal to h by p, correct, which is nothing but h by mv, and p is equal to mv, right? So we know that now we know that p is equal to mv. So second formula becomes lambda is equal to h by mv. What will be the third formula, guys? What is the third formula? The third formula is lambda is equal to root over h square divided by 2m ke. That's something that we just recently did. Okay, all right. Yes, if it is 2m ke, that means that I can also write it as lambda is equal to root over h square divided by 2m. Just think, what is k? Q multiplied with v? Absolutely. QV. Make sense, nonsense? Yeah? Alright. Now, what else? QV also gives you potential difference, if you remember. QV is kinetic energy is equal to QV. QV is your potential difference. V is your potential difference. Okay. Now, for an electron, if lambda is equal to, let's do this. Lambda will be equal to 12.24 divided by I hope this is right. Is this it? No. This has to be root over. Yes. Next formula. What is our next formula? Next formula is 2 pi r. Circumference is equal to n lambda. Don't forget that. 2 pi r is equal to n lambda. Right? Yes. N is the number of wave number. MVR is equal to nh by 2 pi, and all of that you can do. If you solve it, you will get it. Right? Whew, okay. We are almost at the end of it, guys. Heisenberg's uncertainty principle. What did Heisenberg said? What did Heisenberg say? He said a very amazing thing, and the thing was that the exact position and the momentum of a very fast moving particle cannot be calculated precisely at the same time. Amazing, no? What he said? He said that we can never determine the exact position and the momentum of a fast moving object at the same time. And that is why we have written that delta x dot delta p. What is delta x? Delta x is basically the position. Okay, this is the position, right? What is this? This is the momentum. It is always greater than or equal to h by 4 pi. Got it? H by 4 pi. That's it. That's what he said. Okay. Now what is delta p? We know that delta p is what? M. M is mass. Mass is something that where there is no difference, where we cannot put a delta there, right? So we will put delta with velocity. MV. mv is the one. So we'll put m multiplied with the delta v, that is also equal to h by 4 pi. Here delta x is uncertainty's position, delta v is uncertainty in velocity. Gotcha, great, understood. Understood, absolutely understood. Yeah. Now tell me something. Can I also modify it a little bit and I can write it as delta x dot delta p, and then if I multiply and divide it by delta t, then what will happen? If I multiply and divide it by delta t, don't you think that I will get delta E dot delta t? Chalo, understand what I am saying, okay? What I am saying is, so this is my normal this thing, right? Yes. From here, if I multiply and divide by delta t, I will get something like delta t into delta x into delta p divided by delta t is equal to or greater than h by 4 pi, right? If I take it like this, then I can write this t dot position, time into position, yes, time into position, and then momentum by t, right? T delta t dot delta x dot delta p by delta t, correct? Yes. So that means that I can also write it as for delta t dot delta x, okay, delta t dot delta x, it can be again greater than or equal to h by 4 pi, sorry, yes, which means that nothing but this is delta t into, what am I saying, delta t, okay, that means uncertainty in energy, uncertainty in time will also be equal to h by 4 pi. This is also something that you can write, yes, just remember all of these guys, just remember all of these, okay, alright, just remember all of this, great. Now we have come to something called as Bohr principle or Bohr rule. What did Bohr say? He said that you have to fill the lower energy first, okay, what did he say? He said that you have to fill the lower energy first, filling of lower energy first, filling lower energy first, or basically he said that until and unless you haven't, okay, until and unless you haven't done basically, actually you know what, I'm forgetting something. I think I wanted to say something else also here which I have forgotten. I possibly haven't said it. I just wanted to check, is there something that I missed out on? Can't remember. Anyway, forget it. Chalo. Let's. I don't think I have forgotten something. Anyway, we'll see if we have missed out on something. Okay. Anyway, so filling of the lower energy first. Basically, what he means to say is that until and unless you haven't filled this, you can't go jump here. So until and unless I haven't stepped on the number 1 staircase, do you think that I can directly jump to number 10th? I can't. If I have to climb the levels, then I'll have to climb 1, 2, 3, 4. You even cannot jump like without doing your class 11th. Do you think that you can directly get into JEE? No, bro. Not happening. Not happening at all. You have to fill the lower energy first. Okay. So that is why first 1s, then 2s, then 3s, then 2s, then 2p, then 3s. Yes. Then it is what? 3s, then 3p, then 4s. Then it is 3d, 4p, 5s. So basically let me just write it. It is actually 1s, 2s, 2p, 3s, 3p, yes, then 4s, 3d, okay, 4s, 3d, correct, okay, please do remember it. After 3d it is 4p, okay, after 4p it is 5s, after 5s it is, now what, no, 4p then 4d. I think I'm writing it correct, no, 4p, 5s, then 4d, I was right. Okay, after this you can just write it down from here. Okay, after this you can just write it down from here. Now what is Hund's rule? Hund's rule says that electrons fill a subshell singly. They will never pair up first. First they will go for single, 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 and only then they will start pairing it up. So if you can see it here, for 2p, if there are, let's say, if there are 2p3 electrons, then how will you fill it? Will you fill it like this? See, 2p3, right? Will you fill it like this? Wrong. You will not fill it like this. Will you fill it like this? No, you will not. The correct way to fill it will be for 2p, it will be 1, 2, 3. So basically 1, 2, 3 like this. Okay. But if it is, let's say 2p4, how will you start filling up now? It will be 1, 2, 3. So 1, 2, 3 and 3. This is how you are going to fill it. Okay. So just make sure that you are not making a mistake here. Be very careful. Okay. What is Pauli's rule? Pauli said that no two electrons can have all the same 4 quantum numbers. What did he say? He said that no two electrons can have the same quantum number, same all 4 quantum numbers. Okay, it's very important. Can have the same all 4 quantum numbers. Now you are going to ask me, ma'am, what are quantum numbers? So let's go read that also. What are quantum numbers, bacha? Quantum numbers are, okay, now you see there is written something written. So the first one here, this is called as principal quantum number. Okay, this is called as principal quantum number. Okay, yeah. So this will give you the energy shells like K shell, L shell, M shell, L shell, right? So N is, if it is 1, then it is K shell. N, if it is 2, then it is L shell. N is N if it is 3, then it is M shell, and N if it is 4, then it is L shell, right? So it will be K, L, M, N shell it will be, okay, N shell, right? Now comes L. What is this L? This L is called as azimuthal quantum number. What is it called as? Azimuthal quantum number. This value, the value of azimuthal quantum number goes from plus n minus 1. No. I think I made a mistake. One second. No. Just a second. L goes from 0 to continue to n minus 1. This gives you the subshell. I'm a Bengali, please excuse me, sometimes shab comes in, but yeah, it's subshell. Okay, this gives you subshell or sub energy level. So it starts from 0 and goes till n minus 1. So if it starts with 0, and if we are talking about the principal quantum number 2, n is equal to 2, that means it will start from 0 to it will go to 1. If principal quantum number is 3, then it will be 0, 1, 2. Okay. If principal quantum number is 4, then it will start from 0, then it will go to 1, 2, 3. Alright, that's it, done. Now we come to ML. ML is the magnetic quantum number. ML is the magnetic quantum number. This starts from minus n, yes, minus L to plus L. It starts from minus L to plus L, alright. And then the final one is MS, which is called as spin quantum number. Okay, spin quantum number, it can only have 2 values, that is plus half or minus half. That is how the electron is revolving. So the electron can either revolve like this or it can revolve like this. Okay, this is what it is telling. That means in one orbital, in one particular orbital, either the electron can rotate like this or it can rotate like this. Okay, done everybody? Yes, and from here, if you know all of these, you can actually count the total number of electrons. Yes, you can count the number of electrons, you can count which shell it is in, everything can be counted from this quantum number. Okay, now we come to shape of the orbital. The first one here, this is your s orbital. S orbital has a sphere shape. Okay, this is your s orbital. S orbital has a sphere shape. This is your p orbital. P orbital has a dumbbell shape. What is the shape? The shape is dumbbell shape. Okay. Dumbbell shape. Cool. Then comes d orbital. The d orbital here is double dumbbell shape. This is your d orbital, and the d orbital has a double dumbbell shape. Alright, and then f orbital looks even more complex. We do not know what shape is it, so we are not going to talk about it right now. Okay, and then final lap of this chapter. Oh my god, I'm so tired, but yeah, let's continue. Let's complete this. Yeah, we're not going to wait. We're not going to waste time. So quantum mechanical model. Let's continue with this. So here what happens was, there was this person called Schrodinger's cat. You remember all of that? Yeah. So Schrodinger said that he derived an equation which describes the 3D wave motion of an electron. Yes. Now we will not dive too deep into this, but just remember this equation: d square psi divided by x square plus d square psi divided by dy square plus d square psi divided by dz square plus 8 pi square m divided by h square. E minus v psi is equal to 0. Okay. So basically what is it? It's a double partial differentiation. You know that, right? In mathematics you will be doing it. Differentiation is one thing, there is partial differentiation. Yes, and then this is what? Double partial differentiation. Okay. Yes. So x, y, z, what is this x, y and z? X, y and z are the Cartesian coordinates. You know what is Cartesian coordinates. So if I make it like this, then this point will be your x, y and z. Correct? Yes. That's it. Great. What is m here? M is the mass of the electron. What is E? Is the total energy of the electron. What is V? V is the potential energy of the electron. H is the Planck's constant. This is the Planck's constant, and psi is the wave function of the electron. Psi is the wave function of the electron. Now this is all in x, y, z, right? If I take this into polar coordinates, there is also something called as polar coordinates. You will again learn about it in mathematics. If I take it in polar coordinates, yes, I will get something called as r, theta and phi. Okay. Instead of x, y, z, this time I will get as r, theta and phi. So when I put this polar coordinates here, and if I solve it for E and V, if I put different values of E and V, E and V, E and V, then I will get different values of psi, like psi 1, psi 2, psi 3 and dot 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 dot. Yes. Now in mathematics, have you ever seen that when a result comes and you are not able to solve the root and it looks very stupid, it is not satisfying anything, correct? Exactly. So some of those values, some of these psi values will be absolutely, it'll just be stupid. It will not make sense. But there will also be some of those values that will not be stupid, that will actually be meaningful, that will make sense to us, and those values are called as eigenvalues. What is it called? It is called as eigenvalues. You get it? These are called as eigenvalues. Alright everybody, getting it? Yes? Okay? Yes? Amazing. Now, what will happen is, see, what is the significance of psi? What is psi giving us? Right? So let's read it. The wave function may be regarded as amplitude function expressed in terms of coordinates. So basically this wave function, this psi, you can understand it as the most probable function or the amplitude. So when you make that wave, you understand that there is a peak of the wave. And what is that peak of the wave? It is the maximum height that it has, it is the maximum height. What is the maximum height of the curve? Amplitude, makes sense? Nonsense, great, makes sense, okay. So the wave function may have positive or the negative value depending upon the value of the coordinates, and the main aim of Schrodinger equation is to give a solution for probability approach. What we are actually trying to find out is where exactly can we find the electron? What Heisenberg said was that you cannot find the position and the momentum of the electron, the momentum of a fast moving particle at the same point, right? That's what Heisenberg said. But here what he is trying to do is he wants to find out what is the probability. We don't even want to actually find out the position, we just want to know that where might I find the electron, probability, okay. Yes, so when the equation is solved, it is observed that for some regions of space, the value of psi is negative, but the probability must be always positive and it cannot be negative. And that is why we cannot have a negative value. Probability has to be positive, right? Which is why now we stopped using psi and instead of that we started using psi square. Now what is psi square? Psi square is the probability factor, Psi does not really have so much significance. Psi does not have a physical significance at all, in fact. But psi square is important for us. It actually describes the probability of finding an electron within a small space, okay? And the space in which there is maximum probability of finding an electron is called as the orbit. Yes, it's called as its orbital. Getting my point? Yes. Now in quantum mechanical model, let's say that if you, how I told you that you have psi, right? If you solve it for psi r as a function of r, right, you will actually get two parts. You will get radial and angular. Radial plus angular. Now, do you remember that just some time back only we saw that s orbital is sphere in it? Yes. If s orbital is spherical, can you tell me if angular part will be there or not? No. So, can I write it that for s orbital, what will happen? Psi r, radial part will be there, but angular part will not be there, okay. So, I am just writing it angular cross radial, correct. Got it? Yes? Alright. Now, this psi, it cannot give you the spin quantum number, but it can actually tell you all the others. It can tell you the principal quantum number, azimuthal quantum number and the magnetic quantum number, but it cannot give you the spin quantum number. You getting my point? It cannot give you the spin quantum number. It's not possible only, okay. It's not possible at all. Okay. Alright guys, so till here we have understood, just a minute, where is the cursor, yeah? I guess it's just not going to work, anyway, Now the last bit is that we have to find out the graphs and everything, which we will do very fast, okay? We will do it very fast. Oops. Did everything shake? Because the mic actually just got stuck on my shoe and I pulled it very fast. I hope I'm still audible. I am, right? Okay. Alright, yeah. So now what happens is psi square we have understood, right? Yes, we have understood psi square. Yeah. So there are times when what happens is, when the psi square becomes 0. Yes. There are times when psi square becomes 0. If it becomes 0, then do you know what that position is? That particular place is actually called as a node. You're like, node? What is node? Node is actually that space around the nucleus where the probability of finding an electron is almost 0. Okay, where the probability of finding an electron is almost 0 or just 0. Okay, alright. So, what is node? Node is basically, what is node? I am writing it down here. The space around nucleus where, oops, it's you know what, The time is 12 o'clock right now at night when I'm recording, and I think things in the studio are just falling apart. I have no idea if it's working, but I just hope it is. Anyway, so as I was telling, the space around the nucleus where probability of finding electron, okay, where that's called as a node. Now you want to see a you want to see a picture of a node. I'll show you and you will actually understand, okay. So node is always given as n minus 1. Yes, how is it n minus 1? Take a look at it. So you basically add the radial node and the angular node, okay. What do? You basically add the angular node and the radial node, okay. And how do we do that? Check it out. Yes. So see, n minus L minus 1, that's your radial node, plus L if I do, what will it be? L cancel, n minus 1 and that's your node. Funny mathematics, isn't it? So now node can be of two types. There is radial node and angular node. What is radial node? Radial node are, see, these particular places where you cannot find the electron. See, if it is a 3s orbital, in 3s there are 1 and 2, there are two nodes. If it is 1s, there are no nodes. If it is 2s, there is only one node. Got it? Yes, these are your nodes. Alright. Now when it comes to angular node, so at this point, so if I draw this dumbbell, at this part, my chances of finding an electron is almost 0. The electrons are probably here, but not here. So that becomes my angular node, okay? That becomes my angular node. Got it? Now in case of d orbitals, you see the angular nodes are a little more, right? There are more number of angular nodes, okay? Alright, yes. And now finally coming to the graph of it, guys, graph of it. Let's check it out, okay? So final lap of it. Let's just complete it together, everybody. Yes, so variation of radial wave function R with R, okay? What is it? That is basically this capital R is nothing but psi, okay? What is this? Capital R is nothing but psi, okay? So psi with respect to R, this first graph, please just remember it, just draw a rectangular hyperbola. What is this kind of graph? This is called as rectangle hyperbola. Rectangle hyperbola, okay? Now what you have to remember is, because if it is 2s, check it out, very interesting story, okay? Very interesting story. If it is 2s, use the same thing, n minus L minus 1. What is L? L will be equal to 0. From the quantum number, let's see. For L, yes, L will be equal to 0. N is 2, yes, N is 2, N is given to us, L is 0. For N minus L minus 0, so 2 minus 0 minus 1, so it will be 1. Now that here you have 1, understand that same kind of graph you will draw, but what you will do is, see, you will take one dip. See, it is cutting there will be a one node here. Do you see? In case of 2s, we had one node, right? See, you have one node here, right? One node here, right? That's exactly what you are showing. See, one node, one cut. Got it? One cut. Now for 3s, okay, this is for 3s, check it out, n minus L minus 1. So what you can do is, n is 3, L is still 0, minus 1, it will be 2, 3 minus 1 is equal to 2. So now see, 1, 2, 2 cuts. And just like that, you can draw it for 4s, for 5s, for 6s, you can do it for as many times as you want. For s, this is the graph. Okay. Now if I do psi square, do you remember psi square is always going to be positive, negative, negative, positive, negative multiplied with negative, positive, positive multiplied with positive, negative, right? Yes, we are taking psi square, correct? So if I take psi square, now what you have to do is, this graph that you drew, right? Okay, let me show you. See, this graph that you drew, it was like this, right? It was like this. This part is in the negative. This part is in the negative part of the graph, correct? Now, because I am taking psi square, what I will do is, I will draw it like this and this. And exactly that is what we have done. See, the first one remains as it is. Second one, see, that's what I did. That's what I did. See, one I touched it and then went like this. Exactly what happened. Yes. Now see, for this graph, what I have to do is just put it like this, okay? Understand. See. Like this it is going like this, and then it is going like this, right? I have to bring this to the positive part. So what I will do is, check it out, instead of, what I will do is, see, my graph came like this, yes, now it went like this, then it went like this, and then it went like this, yes. Now instead of doing this, I have to bring the negative part to the positive. So what I will do is erase this and then see what I will do. And that's exactly how my graph looks for 3s, right? Yes, got it. Now for 3p, okay, now for 3p also you can remember it. For 3p it's like this, okay, for 3p it's like this, okay, got it. So now you can do it for everyone. Let's just check it out once for 2p. S is done, S is completely covered. If it is 2p, you have to remember this. Please remember this, please remember this. These two, if you remember, done, sorted. You can do the graph for anything and everything. 2p, yes, for 2p it goes like this and then done. Now for 3p if I do, see, n minus L minus 1, n will be 3, what is p? For p what will it be? L will be equal to, what will it be? It will be, come on, yeah, L will be 1 minus 1, so it will be 3 minus 1, 2, so 1. So see, 1 cut and gone. Okay. Now for 4p if I do, see, n minus L minus 1, so 4 minus 1 is equal to 2. See, 2 cuts will be there. 2 cuts will be there. Check it out, see. Like this, 1 cut here and done. Got it? Yeah. And the very same way you can also draw it for 3D. 3D and 2P, they kind of look very similar, okay. 3D and 2P, they look very similar. Gotcha? Okay. And then again the same way what you will have to do is, you can also do it for the 4 pi square r square Vs, you know, the same way. This is what we have done for radial wave. Now if you do again psi square, same thing you have to do. See, 2p remains same. Where is 2p? 2p remains same. Yes, but for 3p if you do, see, 3p, where is it? 3p, see, there was 1 cut at the bottom. All you have to do is just bring it here and then go. See, 3p will be same. See, easy peasy biryani tasty. Yes, now let's solve a question. Chalo. And the final is over. The final lab, this chapter is over, guys. 1 or 2 questions and then we are done. Okay. So the energy of an electron of 2py orbital is greater than 2px? No. Energy will be same, right? Less than 2pz orbital? No. Equal to 2s? No. Same as that of 2px and 2pz? Absolutely right. 2p, x, y and z, they are all at the same level, right? Great. Now, the wave function of this kind of questions do come in JEE, bachcha log, so please take a look at it. The wave function of an orbital is plotted against the distance from the nucleus. The graph represents, see, there are 2 cuts here, guys, 2 cuts. If it is 2 cuts, that means that it can be 3s, right? So n minus L minus 1, that means 3 minus 0 minus 1, if I do, it can be 2. So 2 cuts, yes, it has to be 3s, option C. That's how you solve the graph. Now, if radiation corresponding to second line of Balmer series of Li2 plus ion, if it is second line of Balmer series, that means, guys, so Balmer what happens is, see, if this is my n is equal to 2, If this is my n is equal to 2, this is my n is equal to 3, this is n is equal to 4. So this is the first line of the Balmer series. This is the second line of the Balmer series. That means we are talking about n is equal to 4, okay. So second line of Balmer series of Li2 plus ion knocked out electron from first excited state of H atom. Then kinetic energy of ejected electron would be. You know what? This question, please take it as a homework. Solve it on your own. You will get the PDF, no doubt about it. You will get the PDF. And with this note, I'm going to end the session today. Thank you so much for attending the session. I hope that you have been able to understand everything. Don't forget to like, comment and let us know that how it has helped you. Let us know about the homework problem if you can solve it. Let us know if there was anything that you wanted us to do more. If I have missed out on any topic, I don't think so, but yeah, please do let me know. And if you think that this video has helped you, don't forget to share it with your friends. With this note, lots of love and tara bye-bye. See ya.